right now, wherever you are, lying in the dark, getting comfortable, letting the weight of the day settle into whatever surface is holding you. Two invisible forces are passing through your body. One of them is holding every atom in your skin together, keeping the molecules of the pillow beneath your head from falling apart, sending tiny electrical pulses down your nerves to tell your heart to beat. The other one is gently tugging on a compass needle in a scout's backpack 100 miles from here, guiding migratory birds across continents and shielding the entire planet from the solar wind that would otherwise strip away the atmosphere you're breathing. Two forces, one electric, one magnetic. And here's the thing that still amazes me, even after spending a very long time with this story. For over 2,000 years, human beings watched both of these forces at work, studied them, wrote about them, built devices around them, and never once realized they were the same thing.
2,000 years. The ancient Greeks saw them both, gave them both names, and filed them in completely separate drawers. Medieval navigators relied on one of them to cross oceans, while scholars in parlors amused themselves with the other, and nobody connected them. Some of the sharpest minds in the history of science looked right at the evidence and missed it. And the reason they missed it, the reason the connection stayed hidden for so long, is fascinating in a way that I think will surprise you. Because it turns out the link between electricity and magnetism isn't obvious. It isn't something you can see by staring at a compass or rubbing a piece of amber. The connection reveals itself only under very specific conditions, conditions that nobody stumbled onto by accident for over 20 centuries. And when someone finally did see it, when a compass needle twitched in a way that nobody expected, during a university lecture in Copenhagen in 1820, it cracked open one of the greatest mysteries in the history of science, and set off a chain of discoveries that would, within just 40 years, completely reshape our understanding of light, energy, and the very fabric of space itself. That's what we're going to walk through tonight, slowly, carefully, from the very beginning. How these two forces were born as strangers in the ancient world, how they grew up separately, each developing its own history, its own cast of characters, its own traditions. How the clues that they were related kept piling up for centuries without anyone putting the pieces together. And then, how in a single explosive decade, everything changed, and the wall between them came crashing down. And I want you to think about a few things as we go through this story together. Right now, your heart is beating. That beat with an electrical signal. The phone or the speaker playing this for you is running on electromagnetic waves. The light you switched off before lying down, the warmth of the blanket on your skin, the fact that the mattress beneath you is solid and doesn't collapse into dust, all of it, every bit of it, comes from the same force. One single force, wearing different masks. So the first question is, how is it that something so close to you, something woven into every moment of your life, took humanity over 2,000 years to understand? Why was it so hard to see what was right in front of us? And here's the stranger question. The clues were everywhere. Lightning scrambled compass needles. The same mathematical law governed both electric charges and magnetic poles. People saw these hints, wrote them down, and walked away. So what was it about the connection between electricity and magnetism that made it almost invisible, even to the sharpest minds in the world? Was there something about the way the universe hid this link that was deliberately, almost mischievously, hard to find? And maybe the biggest question of all, when the connection was finally discovered, it didn't just unite two forces, it revealed what light actually is. The light that lets you see someone's face, the warmth that reaches you from the sun across 93 million miles of empty space, that turned out to be made of electricity and magnetism, dancing together. How did we get from rubbing amber on fur to understanding the nature of light? And what does that say about the space you're lying in right now, the dark, quiet, seemingly empty air all around you? We'll get to all of that, but there's no rush. If you drift off somewhere along the way, that's perfectly fine. The story will still be here. It's been here for 26 centuries after all. It can wait a little longer. Let's start where most good stories in science start, with the ancient Greeks. With the shores of the Aegean Sea, where olive trees meet salt water and the light is so clear that you can see islands shimmering on the horizon 60 miles away. And with a man who noticed two strange things happening in that light and had no idea that he was looking at two halves of the same coin. Around 600 years before the Common Era, give or take a few decades, there lived a man named Thales in the city of Miletus, on the western coast of what is now Turkey. Miletus was a busy trading port, a place where ideas moved as freely as goods, and Thales was one of those rare people in the ancient world who tried to explain natural phenomena without reaching for mythology. He didn't want to say that Zeus threw lightning bolts or that Poseidon churned the seas. He wanted mechanical reasons, physical causes. He wanted to understand how the world actually worked, not just what the gods were feeling on any given Tuesday. And Thales noticed two things. Two separate, unrelated, thoroughly puzzling things. The first involved a substance called amber. Amber is fossilized tree resin. It's been hardening in the ground for millions of years, and by the time you find a piece of it, it's this beautiful, golden, translucent stone, light enough to hold in one hand, smooth to the touch, almost warm-looking even in dim light. The Greeks used it for jewelry and decoration, and somewhere along the way, someone discovered something peculiar about it. If you rubbed a piece of amber against fur, against wool, against certain kinds of cloth, and then held it near small light objects, little bits of straw, scraps of dried leaf, tiny feathers, those objects would jump toward the amber and cling to it, as if the amber were reaching out and grabbing them, as if it had suddenly developed a hunger for chaff. Think about how strange that must have looked to someone with no framework for understanding it. You take a piece of golden stone, you rub it on a piece of wool, and now, somehow, the stone can move things without touching them. Small things leap toward it across a gap of empty air. It looked like magic. It looked like the stone had come alive. And in fact, Thales reportedly suggested that amber must contain some kind of soul, some animating force, because only living things were supposed to be able to cause motion. The stone moved things, so the stone must be, in some sense, alive. Now, what Thales was actually seeing was static electricity. When you rub amber against fur, electrons transfer from the fur to the amber's surface. The amber accumulates a net negative charge, and that charge creates an electric field in the space around it. When you bring the charged amber near a small neutral object like a piece of straw, the electric field distorts the distribution of charge within the straw, pulling the straw's electrons slightly away and leaving a slight positive charge on the near side. Since the positive side of the straw is closer to the negative amber, the attractive force is slightly stronger than the repulsive force, and the straw moves toward the amber and sticks. That's electrostatic induction, and we'll come back to it later in much more detail. But Thales, of course, had none of that framework. He just saw something wonderful and weird. The second thing Thales noticed was lodestone. Lodestone is a naturally magnetized mineral, a form of iron oxide called magnetite. You can find it in certain rocks,
especially in a region of ancient Greece called Magnesia, which is actually where the word magnet comes from. And lodestone had its own eerie property. It attracted iron. You could hold a piece of lodestone near an iron nail, and the nail would slide across a table toward the stone and cling to it, just like the amber attracted straw, a force reaching across empty space, pulling things in. And if you suspended a piece of lodestone from a thread, it would slowly rotate until it pointed roughly north-south. Every time, no matter where you tried it. Thales looked at these two phenomena, amber attracting straw and lodestone attracting iron, and he saw two separate mysteries. He noted that both involved a kind of invisible force, a reach across empty space, a pull without contact. But he didn't connect them. He didn't say, these might be related. He didn't even hint at it. They were two different curiosities, filed under two different headings, and that was that. And here's what I find so compelling about this moment. This is the moment the twins were born. Right here, on the shores of the Aegean, in the mind of a philosopher who was trying to understand the world without gods. Electricity and magnetism entered human awareness at essentially the same time, in essentially the same place, observed by essentially the same person. They were born as siblings. And then, almost immediately, they were separated, put in different categories, given different explanations. And for the next 22 centuries, they would grow up apart, developing their own histories, their own communities of investigators, their own bodies of knowledge, never knowing that they were two faces of the same force. The Greek word for amber, by the way, is electron. That's where the word electricity comes from. And the region where lodestone was found, Magnesia, gave us the word magnetism. So even the names we use today, the fundamental vocabulary of the science, carry the fingerprints of that original separation. The twins were named in the same century, by the same culture, and even their names sound like they belong to entirely different families. Now, for a very long time after Thales, not much happened with either of these phenomena, at least not in the systematic, experimental sense that we'd recognize as science. The ancient world had other things on its mind. Wars, empires, philosophy, art. Electricity, the amber trick, remained a curiosity, a parlor amusement, a thing you might show a guest after dinner. Nobody investigated it deeply. Nobody tried to measure it or control it, or figure out what was really going on. It was just one of those odd things the world did sometimes. The Romans, who were brilliant engineers and architects and administrators, but not especially interested in theoretical questions about invisible forces, barely mentioned the amber effect. Pliny the Elder, writing in the 1st century, noted that rubbed amber attracted chaff, and also that a gemstone called lincurium, probably tourmaline, could do the same thing when heated. But he recorded these as facts, not as puzzles to be solved. They went into his natural history, alongside observations about exotic animals and distant lands. One more strange thing in a world full of strange things. Nobody built on them. Nobody followed up. For roughly 15 centuries after Thales, the amber effect was a footnote, an occasional mention in encyclopedic works, never the subject of sustained inquiry. And think about what that means in human terms. Generations of people lived and died. Entire civilizations rose and fell. The Roman Republic became an empire, and the empire collapsed. Christianity spread across Europe. The Islamic Golden Age produced extraordinary mathematics and optics and medicine. The medieval period built cathedrals and universities. And throughout all of it, the amber trick sat there gathering dust, waiting for someone to take it seriously. 15 centuries of not asking why. Magnetism, meanwhile, got somewhat more attention, and for a very practical reason.
that compass property. The fact that a suspended piece of lodestone or a needle that has been rubbed against lodestone points north. Because if you can find north reliably, you can navigate. And navigation matters when your livelihood, or your life, depends on crossing open water. The Chinese were the first to figure this out. The earliest references to magnetic direction finding in China date back to the Han Dynasty, around the 2nd century before the Common Era, though these early devices may have been used more for geomantic purposes, the practice of feng shui, than for navigation. By the Song Dynasty, in the 11th century, Chinese navigators were definitely using magnetized iron needles to find direction at sea. The technology was ingenious in its simplicity. You took a thin iron needle, rubbed it against a lodestone to magnetize it, and then either floated it on a small piece of straw on the surface of a bowl of water where it would slowly rotate to point north-south, or suspended it from a fine silk thread. Either way, the magnetized needle became an arrow pointing toward the pole, a tiny sliver of certainty in the vast uncertainty of the open ocean. The compass reached Europe by the 12th century, probably traveling along the Silk Road and through Arab intermediaries, though the exact path of transmission is still debated. European sailors adopted it eagerly and improved on the design, eventually mounting the needle on a pivot inside a sealed housing, which made it more practical for use on rolling, pitching ships. The compass card, with its 32 points marking directions, became a standard feature. By the 15th century, the compass was indispensable to European maritime exploration, enabling the voyages that would connect continents and reshape global history. But here's the thing, and this matters deeply for our story. Nobody understood why the compass worked. Sailors knew that a magnetized needle pointed north. They knew you could magnetize an iron needle by rubbing it against a lodestone, and that the magnetism would fade after a while. They knew that magnets had two ends, and that like ends repelled, while opposite ends attracted. They knew all of this from practical experience, the same way a carpenter knows wood without understanding botany. But the underlying mechanism was a complete mystery. Some medieval scholars thought the needle was attracted to the North Star. A few believed there was a giant magnetic mountain somewhere at the North Pole, pulling compass needles toward it. Others speculated about cosmic sympathies, invisible affinities between substances, the idea that certain materials were drawn to each other by a kind of natural kinship. These explanations sound quaint to modern ears, but keep in mind that these people had no concept of fields, no understanding of atomic structure, no theory of forces that act at a distance through empty space. They were genuinely trying to explain something that had no obvious explanation. There was one medieval scholar who came closer than most to doing real experimental work on magnetism, and he deserves a brief mention. In 1269, a French soldier scholar named Petrus Peregrinus, Pierre de Maricourt, wrote a letter to a friend while besieging a city in southern Italy. The letter, called the Epistola de Magnete, was a remarkably clear and careful description of magnetic phenomena. Peregrinus experimented with a spherical lodestone, placing a small iron needle at various points on its surface and marking the directions in which the needle pointed. He found that the lines of direction all converged at 2 points on the sphere, which he called poles, borrowing the term from geography. He noted that like poles repel and unlike poles attract. He even noticed that if you break a magnet in half, each half immediately becomes a complete magnet with its own north and south poles. You can never isolate a single pole. Cut the magnet again, and you get 4 complete magnets, each with both poles. Always pairs, never singles. This observation, which seems so simple when you first encounter it, is actually profoundly important and deeply mysterious. It means there are no magnetic monopoles, no isolated north or south poles existing independently. Every magnet, no matter how small, always has both. This fact would eventually become one of Maxwell's 4 equations, but in 1269, it was just a curious thing Peregrinus noticed while sitting outside a besieged city wall with a piece of lodestone and an iron needle. Peregrinus did his work with magnets alone. He never mentioned amber. He never thought about electricity. Why would he? He was a practical man interested in a practical phenomenon, the compass. And he advanced the understanding of magnetism considerably. But the other twin, the electric twin, was invisible to him. Not because he was incurious, but because there was no reason to look. And all this time, for all those centuries, nobody looked at a compass and thought about amber. Nobody looked at the way a magnetized needle pulled on iron filings and said, "You know, this reminds me of what happens when you rub amber on fur and hold it near straw." The two phenomena lived in entirely separate mental compartments. The amber trick was a curiosity for philosophers. The compass was a tool for sailors. And the wall between them was not just conceptual, but social. Different people, different communities, different traditions, working on different problems, never comparing notes. The twins, separated at birth, were growing up in different households, speaking different languages, unaware of each other's existence. And the first person who would have a real chance to connect them, the first person with the skills and the temperament, and the access to both sets of evidence, wouldn't come along for another 2,000 years after Thales. His name was William Gilbert. He was a physician to the Queen of England. And he would study both electricity and magnetism more carefully than anyone before him. He would map them, test them, compare them. And then, in a decision that would shape the course of science for the next 2 centuries, he would declare, firmly and explicitly, that they were fundamentally different. He would build the wall between them even higher, and almost everyone would believe him. William Gilbert was born in 1544 in Colchester, a town in southeastern England. He studied at Cambridge, trained as a physician, and over the course of a distinguished career, rose to become the personal doctor to Queen Elizabeth I. So he had resources, he had prestige, and he had a deeply curious, deeply methodical mind. In his spare time, which for a royal physician was not abundant, he performed experiments. Lots of them. He tested things, he built apparatus, he kept records. And his great passion, the subject that consumed him for nearly 2 decades, was magnetism. In 1600, Gilbert published a book called De Magnete, On the Magnet, and it's one of the landmark works in the history of science. What made it remarkable wasn't any single discovery, though there were several important ones. What made it remarkable was the approach. Gilbert didn't just sit in a chair and theorize about magnetism the way medieval scholars had done. He got his hands dirty. He carved a lodestone into a sphere, a perfect ball of magnetic stone, and he called it a terrella, a little earth. Then he took a small compass needle and moved it slowly across the surface of the terrella, noting how the needle oriented itself at different positions. And what he found was beautiful. Near the equator of the terrella, the compass needle lay flat, parallel to the surface. As he moved toward the poles, the needle tilted, dipping more and more steeply. At the poles themselves, it stood straight up, pointing directly into the stone. The pattern was unmistakable. The compass needle on the surface of the terrella behaved exactly the way compass needles behave on the surface of the actual Earth. Near the geographic equator, compasses lie flat. Near the poles, they dip. The angles matched. Gilbert drew the only reasonable conclusion. The Earth itself is a giant magnet. That's why compass needles point north. There's no magnetic mountain at the North Pole. There's no pull from the North Star. The planet itself is magnetized, with magnetic poles roughly aligned with its geographic poles, and every compass needle on its surface is simply responding to the Earth's own magnetism. This was a profound insight, maybe the single most important idea in the history of magnetism before the 19th century. It took magnetism from the realm of cosmic mystery and grounded it in the physical reality of the planet. The Earth is a magnet. Your compass is responding to the same force that Gilbert mapped on his little stone sphere. Gilbert also investigated the phenomenon of magnetic dip, the way a compass needle tilts downward from horizontal as you move toward the poles. He measured the dip at different latitudes on his terrella and compared the results to observations made by navigators at different latitudes on the actual Earth. The agreement was remarkably good. It was additional confirmation that the Earth is a magnet, and it gave navigators a new tool. By measuring the dip angle of a compass needle, you could estimate your latitude. This wasn't as precise as astronomical methods, but it worked on overcast days when you couldn't see the sun or stars, and in the age before reliable chronometers, any additional navigational data was precious. And Gilbert studied something else that was puzzling navigators: magnetic declination. The fact that compass needles don't actually point to true geographic north. They're off by a few degrees, and the amount varies depending on where you are on the Earth's surface. In London in Gilbert's time, the declination was about 11 degrees east, meaning the compass pointed slightly east of true north. Gilbert documented this and tried to explain it, though he didn't fully succeed. The complete explanation would have to wait for the understanding that the Earth's magnetic poles don't quite coincide with its geographic poles, and that the magnetic field has a complex, irregular structure that shifts slowly over time. But Gilbert was the first to take the problem seriously and try to address it with data rather than speculation. But Gilbert did something else in De Magnete that's crucial for our story. He didn't just study magnetism, he also investigated electricity. He was thorough. He tested dozens of materials to see which ones could be excited by rubbing, the way amber could. And he found that it wasn't just amber. Glass could do it. Sulfur could do it. Sealing wax, various gemstones, and certain resins could all be charged by friction and made to attract light objects. He coined a term for these materials. He called them electrics, from the Greek word for amber, electron. Materials that couldn't be charged this way, like metals, he called non-electrics. And in making these observations, Gilbert essentially founded the systematic study of electricity as a scientific pursuit, giving it its name and its first catalogue of materials. But here's where the story takes a turn that would echo for centuries. Having studied both magnetism and electricity more carefully than anyone before him, Gilbert came to a firm conclusion about the relationship between them. He said they were fundamentally different. Completely different, not related at all. Magnetism, in Gilbert's view, was deep and powerful and cosmic. It was connected to the very soul of the Earth. It could act through barriers, through water, through stone.
Magnetic force was orderly, directional, pointing toward the poles in consistent patterns. It had a grand planetary significance. Electricity, by contrast, was superficial. It was a surface effect, caused by rubbing, limited to certain materials, easily disrupted by moisture, weak, trivial, interesting mainly as a curiosity. It didn't have the depth or the dignity of magnetism. It was, in Gilbert's memorable phrase, like the difference between a living soul and a mere material effluvia, a vapor that rubbing released from the surface of a material. And honestly, looking at the evidence Gilbert had, you can see why he reached this conclusion. With the crude tools available in 1600, with no batteries, no sensitive instruments, no understanding of atoms or electrons or fields, there was no obvious connection between what happened when you rubbed amber on fur
and what happened when a compass needle pointed north. The two phenomena looked different, behaved differently, affected different materials, and followed different rules. Gilbert wasn't being foolish or lazy, he was being careful, and with the information he had, his conclusion was defensible. But it was wrong. And because Gilbert was so thorough, so prestigious, so convincing in his arguments, his separation of electricity and magnetism became the accepted wisdom for generations. He didn't just fail to connect the twins, he built a wall between them and posted a guard. After de Magnet, anyone who might have wondered whether electricity and magnetism were related would have had to push back against the authority of the most respected work on the subject, written by the Queen's own physician. That's a high bar. So as the 17th century began, the twins were more separated than ever. Magnetism had its champion in Gilbert. Electricity had barely begun to be studied at all. And the wall between them, now reinforced with the bricks of scientific authority, looked like it would stand forever. What nobody could have predicted was that over the next century and a half, electricity was about to have an awakening of its own, a period of spectacular discovery, wild experimentation, and genuine brilliance that would bring it from obscurity to center stage. And along the way, clues about its hidden connection to magnetism would begin to pile up, quietly, in the margins of the story, noticed by some, ignored by most, waiting for someone with the right eyes to see them. For the first 100 years or so after Gilbert, electricity developed slowly. A few experimenters built machines that could produce static charge more efficiently than rubbing amber by hand.
Otto von Guericke, the same German engineer who famously demonstrated the power of vacuum with the Magdeburg hemispheres, built a device around 1660 that involved a spinning ball of sulfur that you could charge by holding your hand against it as it rotated. Francis Hawksby, working at the Royal Society in London around 1705, improved on this with a spinning glass globe that produced impressive sparks and glowing effects when charged. These were steps forward, but they were small ones. The real leap came in the 1720s and 30s, when an English experimenter named Stephen Gray made a discovery that seemed simple, but was actually revolutionary. Gray was an interesting character, a dyer by trade, not a university professor or a gentleman of independent means, but a hands-on craftsman who became fascinated by electricity and pursued it with a doggedness that his more privileged contemporaries sometimes found charming and sometimes found slightly embarrassing. He was elderly and not wealthy when he did his most important work, often relying on the hospitality of friends who gave him space and materials to experiment with. What Gray found was that electric charge could be transmitted from one object to another through certain materials. He started with a glass tube, charged by rubbing, and discovered that if he inserted a cork into the end of the tube, the cork itself became electrified. It could attract small feathers and bits of leaf, even though nobody had rubbed the cork. The charge had flowed from the glass into the cork through direct contact. Gray then attached a long piece of thread to the cork, dangling an ivory ball at the far end, and found that the ball at the end of the thread could also attract feathers. The charge had traveled along the thread, but not along every thread. When Gray used silk to suspend his apparatus, the charge stayed where he wanted it. When he used brass wire or damp string, the charge leaked away. Some materials allowed charge to flow through them freely, others blocked it. Gray had discovered the difference between conductors and insulators, although he didn't use those terms. Metals, water, the human body, these conducted electricity. Glass, silk, dry air, amber itself, these insulated it, holding charge in place. This distinction, which seems so obvious to us now that we teach it to children, was genuinely new. It meant that electricity wasn't just a property of a rubbed surface. It was something that could move, something that could flow from place to place, something that could be channeled and directed like water through pipes. Gray even demonstrated, in a famous experiment, that a human being could be electrified. He suspended a boy from silk ropes, essentially insulating him from the ground, and then touched a charged glass tube to the boy's feet. The charge flowed through the boy's body, and small objects placed near his face and hands jumped toward him. The flying boy experiment became a popular public demonstration, and while it was mainly treated as entertainment, it made an important scientific point. The human body is a conductor. Charge flows through us. We are part of the electrical world, not separate from it. Around the same time, a French chemist named Charles-François de Cisternay-Dufay was conducting his own series of careful experiments.
Dufay was more systematic than Gray, more inclined to classify and categorize. And he noticed something that Gray had missed. When Dufay rubbed glass with silk and brought it near another charged object, sometimes the objects attracted each other and sometimes they repelled. The pattern, when he traced it carefully, was consistent. Glass rubbed with silk produced one kind of electricity. Resin rubbed with fur produced another kind. If you brought two glass-charged objects together, they repelled. Two resin-charged objects repelled. But a glass-charged object and a resin-charged object attracted each other. Dufay concluded that there were two distinct types of electricity. He called them vitreous electricity, from the Latin for glass, and resinous electricity, from resin. Each type attracted the other and repelled its own kind. This was the first clear articulation of one of the most fundamental facts about charge. There are two types, and like charges repel, while unlike charges attract. A principle so basic that you might have learned it in grade school. But someone had to discover it first, and Dufay was the one who nailed it down experimentally, through patient work with charged rods and hanging threads and careful notes in the 1730s. So by the mid-1700s, electricity was picking up momentum. People knew that charge could be produced by friction, that it came in two types, that it could be conducted through certain materials but not others, and that like charges repelled, while unlike charges attracted. All useful knowledge, all building blocks. But the understanding was still fragmented, still mostly qualitative, still lacking any kind of unifying theory. And then, in 1745, something happened in a laboratory in the Netherlands that changed the game entirely and turned electricity from a scientific curiosity into a genuine sensation. A scientist named Peter van Musschenbroek, working at the University of Leiden, accidentally invented a device that could store electric charge. The accident was instructive in itself. Musschenbroek was experimenting with water in a glass jar, trying to electrify the water using a friction machine. He held the jar in one hand, while a wire from the friction machine dipped into the water. When he happened to touch the wire with his other hand, completing a circuit through his body, he received a tremendous shock. A jolt so violent, so unexpected, so thoroughly unpleasant, that he later wrote to a colleague that he wouldn't repeat the experience for the entire Kingdom of France. What Musschenbroek had stumbled onto was a capacitor, though nobody would call it that for a long time. The device became known as the Leyden jar, named after the university where it was invented, and within months, it was being replicated in laboratories across Europe. The recipe was simple enough that anyone with a glass jar and some metal foil could build one. In its standard form, it was a glass jar coated inside and out with metal foil, with a metal rod poking through a cork at the top, connected to the inner foil by a chain or wire.
You charged it up using a friction machine, feeding charge into the inner foil through the rod, and the jar would hold that charge, store it, keep it ready until you provided a path for it to discharge. When it did discharge, all the stored energy came rushing out at once in a dramatic, painful, and occasionally dangerous spark. The Leyden jar changed the scale of electrical experiments overnight. Before it, experimenters worked with tiny charges and feeble attractions. The Leyden jar gave them real power. Visible arcs of light that could leap several inches. A crack loud enough to startle an entire room. A shock that could knock a grown man off his feet and leave his arm numb for hours. Some experimenters, caught off guard by an unexpected discharge, were thrown across their laboratories. The Leyden jar turned electricity from a curiosity into a spectacle, from a parlor trick into something that could hurt you. Now, what was actually happening inside the Leyden jar in terms of our modern understanding is worth pausing on for a moment, because it introduces an idea that matters for the rest of the story. When you charge a Leyden jar, you're pushing excess charge, electrons, onto the inner foil. That charge creates an electric field through the glass, and that field pushes charges around on the outer foil, driving electrons away and leaving a positive charge on the outer surface.
So you end up with negative charge on the inside, positive charge on the outside, and between them, through the glass, an intense electric field. The energy isn't really stored in the charges themselves. It's stored in the electric field between the foils. This is a subtle but important point, and it connects directly to Faraday's later insight that fields are real things that carry energy. But nobody understood this in 1745. They just knew they had a jar that could give you the shock of your life. And scientists, being scientists, immediately started doing outrageous things with it. Jean-Antoine Nollet, a French physicist who was equal parts brilliant researcher and natural showman, performed a legendary demonstration before King Louis XV in 1746. He arranged 180 of the king's royal guards in a line, each man holding hands with the one beside him, forming a human chain. Then Nollet discharged a Leyden jar through the chain. All 180 soldiers jumped simultaneously, involuntarily, their muscles jerking from the electrical pulse passing through their bodies. The king was reportedly delighted. I imagine the guards were somewhat less amused. But Nollet wasn't just putting on a show. He was making a point. Electricity could travel through the human body. It could leap across the contact between one person's hand and another's. It was fast, maybe instantaneous. It was powerful, and it could be accumulated and released at will. Electricity was no longer a curiosity. It was a force to be reckoned with. And the person who did more than anyone else to make sense of it all, to take the scattered observations and the dramatic demonstrations and weave them into something approaching a coherent theory, was working not in a European university, but in a print shop in Philadelphia. His name was Benjamin Franklin, and whatever you may have heard about kites and keys and thunderstorms, his actual contributions to the science of electricity were far more important and far more interesting than the mythology suggests. Franklin started experimenting with electricity in the mid-1740s after attending a demonstration of electrical effects by a traveling lecturer. He acquired some Leyden jars and a friction generator, and he dove in with the intense practical curiosity that characterized everything he did. Within a few years, he had developed a theory of electricity that was remarkably clear and, in its broad outlines, surprisingly modern. Here's what Franklin proposed. He said that electricity was a single fluid, present in all matter. Every object contained a certain normal amount of this fluid. When you rubbed amber with fur, you weren't creating electricity from nothing. you were moving it, transferring it from one object to another.
The amber gained an excess of the electrical fluid, and the fur lost some. The total amount stayed the same. You could rearrange it, but you couldn't create or destroy it. Think about how important that idea is. Franklin was articulating in his own way what we now call conservation of charge. The total charge in a closed system doesn't change. You can move charge around, you can separate positive from negative, but the total is constant. This principle is one of the bedrock foundations of physics, and Franklin arrived at it through careful observation and clear thinking, decades before anyone had the mathematical tools to formalize it. Franklin also introduced the terminology that we still use today, everywhere, in every physics classroom and every circuit diagram on the planet. He called the condition of having excess electrical fluid positive. He called the condition of having a deficit negative, plus and minus.
These terms, these symbols, the plus sign on one terminal of a battery and the minus sign on the other, they all trace directly back to Benjamin Franklin, sitting in his study in Philadelphia in the 1740s, trying to make sense of what he was seeing. Now, Franklin made one mistake in his theory, and it's a small irony that has caused confusion ever since. He guessed that the electrical fluid flowed from positive to negative, from the place with excess to the place with deficit. That seemed logical. Fluid flows from where there's more to where there's less, the way water flows downhill. But when electrons were eventually discovered about 150 years later, it turned out that they carry negative charge, and they flow from negative to positive, from the deficit to the excess. The actual movement of charged particles goes in the opposite direction from what Franklin assumed. So what we now call conventional current, the direction we draw current flowing in circuit diagrams, is the opposite of the actual electron flow. Every electrical engineer in the world works with this backwards convention every single day. And it's all because Franklin, working with no way to check, happened to pick the wrong direction. By the time anyone could verify it, the convention was so deeply embedded in the scientific literature that changing it would have caused more confusion than keeping it. So we kept it. A 280-year-old guess, wrong in its specifics, but brilliant in its framework, still shaping how we draw diagrams and teach circuits today. There's one more thing about Franklin's framework that's worth pausing on, because it resolved a question that had been hanging in the air since Dufay. Remember, Dufay had identified two types of electricity, vitreous and resinous. Franklin replaced this with his single fluid theory, arguing that there was only one kind of electrical fluid, and what Dufay had interpreted as two different types were really just excess and deficit of the same stuff. Vitreous electricity, the kind produced by rubbing glass, was a positive charge, an excess of fluid. Resinous electricity, from rubbing resin, was a negative charge, a deficit of fluid. Same fluid, different amounts. This was a simplification, and like many simplifications in science, it was partly right and partly misleading. Franklin was correct that there's a deep sense in which positive and negative charges are two sides of one coin, related by the presence or absence of something. But the thing whose presence or absence matters is electrons, which wouldn't be discovered for another 150 years. A positively charged object isn't one that has excess fluid, it's one that has lost electrons. A negatively charged object has gained electrons.
The fluid that moves is made of electrons, and it flows from negative to positive, opposite to what Franklin assumed. But the brilliance of Franklin's framework was in its structure, not its microscopic details. He established that there are two states of charge, that they're complementary, that they attract each other, that like states repel, and that the total amount is conserved. All of those structural features turned out to be exactly right,
and they provided the scaffolding on which all subsequent understanding was built. Sometimes getting the architecture right is more important than getting the bricks right. But Franklin's most famous contribution, and the one that matters most for our story about the twins, was his work on lightning. Franklin suspected, based on a series of careful observations, that lightning was electrical in nature, that the dramatic bolts of light splitting the sky during a thunderstorm were the same phenomenon as the sparks jumping from a Leyden jar, just on an incomparably larger scale. This was a bold claim. Lightning was terrifying, godlike, seemingly beyond human comprehension. To say it was the same thing as the crackle from a rubbed glass rod, just bigger, was almost audacious. But Franklin designed an experiment to test it. The famous kite experiment, probably conducted in June of 1752, though the exact details are debated, and some historians think it may have been performed slightly differently than the popular story suggests. The key point is that Franklin, or his associates, managed to draw electrical charge from a thundercloud and show that it behaved exactly like the charge produced by friction machines and stored in Leyden jars. Lightning was electricity. The sky was a giant Leyden jar, charging up through the movement of air and water and discharging through those spectacular, terrifying bolts. Now, here's something that matters for our twin story, something that was noted at the time but not fully appreciated. Sailors had long reported that when lightning struck a ship, the ship's compass needles sometimes went haywire. They'd reverse polarity, north becoming south, or deflect wildly and take hours to settle back to normal. This happened often enough that it was well documented in maritime records. Lightning, which Franklin had now proven was electrical, was doing something to magnets. An electrical event was affecting a magnetic device. If you were looking for a connection between electricity and magnetism, this was a clue. A big, flashing, obvious clue. An electrical discharge from the sky was reaching into the compass and scrambling the magnetic alignment of the needle. What could be more suggestive? And yet, almost nobody followed up on it. The observation was noted, recorded, filed away, and largely ignored. Because everybody already knew, everybody had known since Gilbert, that electricity and magnetism were fundamentally different phenomena. If lightning messed up compass needles, that was just one of those anomalous things that happened sometimes. An oddity, a footnote, not evidence of a deeper truth. The twins were sending signals to each other across their separation, and nobody was listening. There were other clues too, scattered through the 18th century like breadcrumbs on a forest path. In 1735, a man in Wakefield, England, reported that a lightning bolt had struck a box of knives and forks, and the knives had become magnetized. In 1751, Benjamin Franklin himself magnetized a sewing needle by passing the discharge from a Leyden jar through it. He noted the result and moved on. He didn't ask why an electrical event should create magnetism in a piece of steel. He just filed it as an interesting observation. Think about how close that is. Franklin, one of the sharpest minds of his century, held in his hands a needle that had been magnetized by electricity. The two forces, the two twins, had interacted right in front of him, in his own laboratory, and he set the needle down and went on to other things. He was so deeply embedded in the assumption that electricity and magnetism were different forces that even when he saw them interact, it didn't register as significant. That's the power of a paradigm. When everyone agrees that two things are separate, evidence to the contrary looks like noise. And so the 18th century rolled on, and the clues kept piling up, and nobody connected them, and the wall between the twins held firm. Until, very quietly, in a laboratory in Italy, a dispute about frogs opened a door that nobody knew was there. While electricity was having its dramatic coming of age in the 1700s, with Leyden jars and flying kites and soldiers jumping in unison, a deeper question was quietly waiting to be answered. Everyone could see that charged objects pushed and pulled on each other. Everyone knew that the force was stronger when the charges were closer together. But what was the exact mathematical law? How precisely did the force depend on the distance? How did it depend on the amount of charge? Without precise measurements, electricity would remain a qualitative science, impressive to watch but impossible to calculate or predict. And the study of charge itself was getting more precise. And the person who brought that precision to its sharpest point was a French military engineer named Charles-Augustin de Coulomb. Coulomb was born in 1736 into a well-to-do family in Angoulême, in southwestern France. He studied mathematics and engineering at the prestigious École du Génie at Mézières, one of the best engineering schools in Europe, and served as a military engineer for several years, including a long posting to Martinique in the Caribbean, where he oversaw fortification construction in difficult tropical conditions. The posting damaged his health, but sharpened his practical engineering skills, and when he returned to France, he turned increasingly toward pure scientific research. He was meticulous, patient, and mechanically gifted. The kind of person who could design and build instruments of extraordinary delicacy and then use them with extraordinary care. He had a gift for reducing complex problems to simple, measurable configurations, and the apparatus he designed to measure electrical and magnetic forces, the torsion balance, is a masterpiece of experimental simplicity. Here's how it works. Imagine a thin fiber, a silver wire or a silk thread, suspended vertically from a fixed point at the top of a sealed glass cylinder. At the bottom of the fiber, attached horizontally like the beam of a balance, is a light rod. On one end of the rod is a small charged sphere. On the other end is a counterweight. Now, bring a second charged sphere close to the first one. The electric force between them will push the rod, twisting the fiber. By measuring how much the fiber twists and knowing the fiber's resistance to twisting, you can calculate the force between the two charged spheres. Coulomb used this apparatus to make the first precise measurements of the electric force between charges, and what he found was clean, elegant, and deeply important. The force between two charged objects follows an inverse square law. If you double the distance between them, the force drops to a quarter. Triple the distance, and it drops to a ninth. The force is proportional to the product of the two charges, and inversely proportional to the square of the distance between them. If you've taken any physics at all, you've probably seen this written as F equals K times Q1 times Q2 divided by R squared. That's Coulomb's law. It's one of the fundamental equations of physics, and it describes the force between any two charged objects anywhere in the universe. And there's something else lurking inside Coulomb's measurements that wouldn't be fully appreciated for over a century. He was measuring the force between charges as if charge were a continuous quantity, something you could have any amount of, like water in a bucket. But it turns out, charge comes in fixed, indivisible packets. The smallest possible unit of charge is the charge carried by a single electron, an amount so tiny that everyday objects contain quintillions of them. When you shuffle across a carpet and touch a doorknob and feel that little snap, you've transferred a few billion electrons. A few billion sounds enormous, but compared to the quintillions in even a modest static charge, it's a rounding error. The charge on any object, anywhere, is always a whole number multiple of the electron's charge. Never a fraction. Never 1.5 electrons worth. Always a whole number. This property, quantization,
wouldn't be understood until the 20th century, but it was always there, hidden beneath the smooth curves of Coulomb's measurements, waiting to be found. Now, here's what's interesting. Coulomb didn't just measure the electric force. He also used his torsion balance to measure the force between magnetic poles. He put small magnets on the balance arm instead of charged spheres and measured how they attracted or repelled each other at different distances. And he found the same law, the same inverse square relationship. The magnetic force between two poles drops as the square of the distance, just like the electric force between two charges. Think about what this means from the perspective of our twin story. By the late 1780s, someone had carefully measured both forces and found that they follow exactly the same mathematical pattern, the same inverse square law that Newton had found for gravity. Three forces: gravity, electricity, magnetism, all obeying the same mathematical rule. And two of them, electricity and magnetism, dealing with attractions and repulsions between objects that are, in some sense, analogous. Charges attract and repel. Magnetic poles attract and repel. The math is the same. Wouldn't you think this would have raised some eyebrows? Wouldn't you think someone would have said, "Hold on, these two forces follow the same law. They both involve attraction and repulsion. They're both mediated across empty space without contact. Maybe they're related." And some people did notice the similarity. It was commented on. It was discussed. But nobody took the next step. Because mathematical similarity doesn't prove physical identity. Lots of things in physics follow inverse square laws. The intensity of light drops as the inverse square of the distance from the source. And nobody thinks light and gravity are the same force. The resemblance was noted, acknowledged, and set aside. The wall was still standing. The twins were following the same rules, speaking the same mathematical language, and still, nobody recognized them as family. But the clues were getting louder. And the next one, the one that would finally crack the wall, was about to arrive from a completely unexpected direction. It wouldn't come from a bigger Leyden jar or a more sensitive torsion balance.
It would come from dead frogs, a bitter scientific rivalry, and an Italian physicist who would accidentally invent the most important tool in the history of electrical science. A device that would make steady, continuous electric current possible for the first time. And in doing so, would create the exact conditions needed for someone to finally see what had been hidden for 22 centuries. If you're still with me, take a breath here. We've come a long way already, from ancient Greece to revolutionary France, from amber and lodestone to precision instruments and inverse square laws. We're about to cross a threshold. The story is about to accelerate. The next few decades, roughly 1800 to 1865, will contain more breakthroughs per year than the previous 2 millennia combined. So settle in, get comfortable. And if your eyelids are getting heavy, that's fine. The story flows like a river from here, one discovery pouring into the next, and you can let it carry you. The story of the battery begins, improbably, with a frog's leg twitching on a table in Bologna, Italy. The year is around 1780, and a physician and anatomist named Luigi Galvani is conducting experiments on what he calls animal electricity, the idea that living tissue generates its own electrical force. Galvani was a careful, methodical researcher, a professor of anatomy at the University of Bologna, and his interest in the electrical properties of animal tissue was part of a broader fascination with the relationship between electricity and life. He and his wife Lucia, who was also his laboratory assistant and a skilled experimenter in her own right, worked together, dissecting frogs and applying various electrical stimuli to their exposed nerves and muscles. What Galvani noticed was striking. A dissected frog's leg would twitch when touched with two different metals simultaneously. For instance, if you held the leg with a brass hook and laid it on an iron railing, the leg would jerk. If you touched a nerve with a pair of scissors made of two different metals, the muscles would contract. And if a nearby static electricity machine produced a spark, legs hanging from copper hooks would kick. Galvani interpreted this as evidence that the frog's muscles contained their own inherent electricity, a life force of sorts, stored in the tissue and released by the stimulus. He published his findings in 1791, and they caused a considerable stir, partly because the idea of animal electricity was philosophically attractive, the notion that life itself had an electrical dimension, that the animating force that separated living from dead might literally be a spark, and partly because the demonstrations were dramatic, dead frogs kicking as if alive.
There's something primal about that image, something that touches on the oldest questions about life and death and what separates them. But Galvani had a rival, and his rival's name was Alessandro Volta. Volta was a physicist at the University of Pavia, about 120 miles from Bologna, and he thought Galvani's interpretation was wrong. Volta argued that the electricity wasn't coming from the frog. The frog was just a very sensitive detector, its muscles twitching in response to a current that was being generated not by living tissue, but by the contact between the two different metals. The electricity, Volta insisted, was coming from the metals, not the animal. The two men argued publicly and passionately for years. It became one of the great scientific feuds of the era. Galvani's supporters saw animal electricity as a profound, almost vitalist principle, evidence that life itself had an electrical dimension, that the spark of life was, in some literal sense, a spark.
Volta's supporters saw this as romantic nonsense, a misinterpretation of a straightforward physical effect. The debate played out in letters, in journals, in public demonstrations, and in the salon conversations of Italian intellectual life. Students took sides. Careers were shaped by allegiance to one camp or the other. And eventually Volta did something brilliant to prove his point. He asked himself, if the electricity comes from the contact between two different metals, do I even need the frog? What if I stack alternating discs of two different metals, copper and zinc, say, separated by pieces of cardboard soaked in salt water, and pile them up into a tall column? The frog, in this picture, was just a detector, a very sensitive, very dramatic detector, but a detector nonetheless. The real source of electricity was the chemical interaction between the metals and the salt solution. Remove the frog, keep the metals, see what happens. In 1800, Volta built exactly that. A stack of copper and zinc discs, separated by brine-soaked cardboard, piled one on top of another. He connected a wire from the top of the pile to the bottom, and current flowed. Steady, continuous, reliable current. Not a spark, not a momentary discharge. A continuous flow of charge through a wire, available as long as the chemical reaction in the pile kept going. The sensation was peculiar and distinctive. If you touched the terminals of the pile with wet fingers, you felt a sustained tingling, quite unlike the sharp snap of a Leyden jar discharge. If you connected the pile to a wire, the wire warmed up. If the wire was thin enough, it glowed. If you put the terminals in a glass of water, bubbles appeared. And if you collected those bubbles carefully, you discovered that they were hydrogen and oxygen. The current was ripping water molecules apart, separating them into their constituent elements. This was electrolysis, and it opened an entirely new approach to chemistry, the use of electrical force to break apart and recombine substances. This was the voltaic pile, the first true battery. Volta announced his invention in a letter to the Royal Society of London in March of 1800. The response was extraordinary.
Scientists across Europe built their own piles within weeks of hearing about it. The battery was easy to construct, requiring only common materials, and the results were immediate and dramatic. You could produce a continuous current that lasted for hours. You could decompose water into hydrogen and oxygen by passing the current through it. You could heat wires to glowing. Humphrey Davy, working at the Royal Institution in London, built increasingly powerful batteries and used them to isolate new chemical elements. Potassium, sodium, calcium, barium, one after another, pulling atoms apart with electrical force. Napoleon himself was fascinated and invited Volta to demonstrate the pile in Paris. The battery changed chemistry, it changed physics, and it changed the world. Within a few decades, it would lead to electroplating, to the telegraph, and eventually to the entire electrical age. But its importance for our specific story, the story of the twins, is even more fundamental than any of those applications. Because before Volta's pile, all the electricity anyone had ever worked with was static. Charges sitting on surfaces, brief sparks from Leyden jars, momentary discharges that were over in an instant. The only electricity anyone had access to was electricity at rest, which is exactly what the word electrostatics means. Charge that is stationary, accumulated, and released in quick bursts. But a battery produces something entirely different. It produces a steady current, a continuous flow of charge through a wire, sustained over time. And a steady current, it would turn out, does something that static charges cannot do. A steady current creates a magnetic field around the wire that carries it. That's the connection. That's the link between the twins. And it had been invisible for 22 centuries for a beautifully simple reason. Nobody had ever produced a steady current before. Static charges don't create magnetic effects that you can easily detect. You need moving charges, flowing charges, current. And current requires a battery, which nobody had until Volta built one in 1800. Think about what that means. The reason Thales couldn't connect electricity and magnetism wasn't stupidity. The reason Gilbert couldn't see it wasn't carelessness. The reason Franklin and Coulomb missed it wasn't lack of intelligence. The connection between electricity and magnetism manifests only when charges are in motion, flowing steadily through a conductor.
And nobody had the technology to make charges flow steadily until Volta invented the battery. The clue had been hidden behind a technological barrier for the entire history of human civilization. You couldn't find it with amber and fur. You couldn't find it with a Leyden jar. You needed a battery. And as soon as the battery existed, the discovery followed almost immediately. Within 20 years of Volta's invention, someone saw the compass needle move. Hans Christian Ørsted was born in 1777 in Rudkøbing, a small town on the Danish island of Langeland. His father was a pharmacist, and young Hans and his brother Anders grew up helping in the family shop, absorbing chemistry and natural philosophy almost by osmosis. He studied at the University of Copenhagen, earned a doctorate in philosophy, and eventually became a professor of physics there. But Ørsted was not just a physicist.
He was also deeply influenced by the German Romantic philosophical tradition, specifically by the ideas of Friedrich Wilhelm Joseph Schelling. Schelling was a philosopher who believed in the fundamental unity of nature. He argued that all the forces of the natural world, electricity, magnetism, gravity, chemical affinity, life itself, were manifestations of a single underlying principle. Nature was one thing, expressing itself in many ways. The apparent diversity of forces was an illusion. Underneath, everything was connected. Now, this was a philosophical conviction, not a scientific one. There was no experimental evidence for it. Most practicing scientists, especially the hard-nosed experimentalists in France and England, would have dismissed it as speculative hand-waving romantic nonsense. But Ørsted believed it, deeply. And that belief shaped the questions he asked and the experiments he designed. Think about how unusual this was.
For over 2,000 years, people had looked at electricity and magnetism and seen two separate things. Gilbert had reinforced the separation with the authority of systematic experiment. Coulomb had characterized them independently with mathematical precision. The entire scientific establishment treated them as different forces that happened to share some superficial similarities. And here was Ørsted, walking into the problem already convinced they must be connected. Not because of any evidence, but because his philosophy told him that all forces must be connected. This is one of those moments in the history of science that makes you think about the relationship between belief and discovery. Ørsted's conviction came from philosophy, not from data. It was, in a strict empirical sense, a prejudice. He believed something before he had evidence for it, and yet that belief led him to design the experiment that produced the evidence. Would someone without that belief have set up the same experiment? Possibly. But the history suggests that it would have taken longer. The people who didn't believe in a connection, who treated electricity and magnetism as separate, had no particular reason to put a compass next to a current-carrying wire. Why would you? If you already know they're different forces, putting a compass near a wire is as pointless as putting a compass near a glass of water. You wouldn't expect anything to happen. Ørsted expected something to happen. He couldn't say exactly what, but he expected it. And that expectation kept him trying, year after year, experiment after experiment, when a less motivated researcher might have given up. He spent years looking for a connection between electricity and magnetism. He tried various configurations, various setups, and got ambiguous or negative results. Part of the problem was that the early batteries were weak, producing small currents.
Part of the problem was that the magnetic effect of a current drops rapidly with distance, so you have to position your compass quite close to the wire to see anything. And part of the problem was that Ørsted, guided by his philosophical expectations, initially looked for the wrong kind of effect. He expected the force to act along the wire, pushing the compass needle to point toward it or away from it, the way electric charges push and pull. That's what a force should do, right? Push or pull in a straight line. And when he positioned his compass that way, the deflection was minimal or absent, because the magnetic effect of a current doesn't work in straight lines. It circles. And he didn't know that yet. And then came April 21st, 1820. This is one of those dates in the history of science that deserves to be remembered the way we remember dates of battles and treaties and revolutions.
Because what happened on this day was, in its own quiet way, as consequential as any of those. Ørsted was giving a lecture to students at the University of Copenhagen. The lecture hall was modest. The audience was small, perhaps a dozen advanced students. He had a battery, a voltaic pile of the improved kind that had been developed in the years since Volta's original design, connected to a platinum wire. The current flowing through the wire was strong enough to heat it visibly, and he had a compass needle sitting on the table, oriented in the usual way, pointing north-south. The lecture was about electricity and heat, the way current flowing through a wire produces warmth. This was a well-known effect by 1820, and Ørsted was demonstrating it as part of his regular teaching. The compass was there, sitting near the wire. Accounts differ on exactly why.
Some say Ørsted had planned to look for a magnetic effect and was using the lecture as an opportunity to test his long-standing hypothesis. Others say the compass happened to be nearby and the deflection caught his eye by chance. The truth probably sits somewhere between these two versions. What happened was this. Ørsted aligned the wire roughly parallel to the compass needle, running north-south, and turned on the current. The compass needle swung. It rotated, settling into a new position that was roughly perpendicular to the wire, pointing east-west instead of north-south. Some accounts say the effect was small, just a tremor, a slight deflection that the students might not even have noticed. Others suggest it was more dramatic, a clear and decisive swing of the needle. What seems clear is that Ørsted recognized the significance of what he was seeing, even if the effect was modest. The compass needle had responded to the electric current.
After 22 centuries, the twins had made contact. Now, whether this was a complete surprise or whether Ørsted had been specifically watching for this effect is debated by historians. Some accounts present it as pure serendipity, a chance observation during a routine lecture. Others suggest Ørsted had been deliberately setting up this demonstration, hoping for exactly this result, based on his philosophical conviction that electricity and magnetism must interact. The truth is probably somewhere in between. He'd been looking for this for years. He'd tried before and gotten nothing clear. But on this day, with a strong enough current and a sensitive enough compass positioned in the right place, the effect was unmistakable. The compass needle moved, not because someone touched it, not because of a breeze or a vibration, because of the electric current flowing through a nearby wire. Electricity was doing something to a magnet. But here's what made Ørsted's observation truly revolutionary. The thing that separated it from every vague hint and ambiguous clue that had come before. The compass needle didn't point toward the wire, and it didn't point away from the wire. It pointed around the wire, perpendicular to it. If you imagine looking at the wire end on, like looking down the barrel of a gun, the magnetic force wraps around the wire in a circle. It curls. This is geometrically different from anything anyone had ever seen in the behavior of forces. Gravity pulls things in straight lines toward masses. Electric forces push or pull charges in straight lines toward or away from each other. But this new magnetic effect created by an electric current, it curved, it circled. It wrapped around the wire like a vine wrapping around a pole. And this is why nobody had found the connection before, even when they were looking for it. Everyone expected that if electricity affected magnetism, it would do so in a straight line way. Push or pull, attract or repel. Along the axis of the wire or directly toward it or away from it. Nobody imagined a curling, circular force. It was geometrically unprecedented. And if you don't know to look for a circular effect, you can position your compass in exactly the wrong spot and see nothing at all. The needle might be aligned with the circular field by chance and show no deflection. Or the current might be too weak, or the compass too far away. The effect is real and reproducible, but it's easy to miss if your experimental setup isn't exactly right. The wall between the twins had just developed its first crack, and it was about to shatter. Ørsted spent the next few months carefully documenting the effect, testing different configurations, different current strengths, different positions for the compass needle. He placed the compass above the wire, below it, to the sides. He reversed the direction of the current and watched the compass needle reverse its deflection. He was meticulous and thorough. In July of 1820, he published his results in a short Latin pamphlet and sent copies to scientific societies across Europe. The reaction was immediate, widespread, and electric. Within weeks, physicists across the continent were reproducing Ørsted's experiment, confirming his results, and then racing to extend them. The news traveled through scientific networks with the speed of a postal service operating at full capacity. Letters were written, pamphlets were distributed, demonstrations were arranged. In London, Humphrey Davy and his assistant Michael Faraday reproduced the effect immediately. In Paris, the scientific establishment was galvanized. In Germany, physicists who had been working on entirely different problems dropped what they were doing and turned to electromagnetism.
Because once you know that electricity and magnetism are connected, once you've seen the compass needle move in response to a current, 100 new questions explode into existence all at once. How exactly does the current create the magnetic effect? What's the precise mathematical law? How does the strength of the magnetic field depend on the current and the distance? Can you wind a wire into a coil and make a stronger effect? Can you build an electromagnet, a magnet you can turn on and off at will? What happens if you coil the wire around an iron core? And the most tantalizing question of all, if electricity can create magnetism, can magnetism create electricity? Can you start with a magnet and somehow get a current to flow? Can you reverse the trick? These questions would keep physicists busy for the next 40 years, and the first person to respond, the one who moved with the most astonishing speed, was a French mathematician and physicist named André-Marie Ampère.
Ampère heard about Ørsted's discovery in September of 1820, just 2 months after the Latin pamphlet was circulated. And within a single week, within 7 days of learning that a current-carrying wire could deflect a compass, Ampère had begun a series of experiments that would go far beyond anything Ørsted had done. To understand Ampère, you have to understand something about the man himself, because his intensity, his driven quality, his almost feverish pace of work didn't come from nowhere. His life had been shaped by tragedy in a way that left deep marks. Ampère was born in Lyon in 1775. He was a prodigy, largely self-educated, devouring books from his father's extensive library. His father, Jean-Jacques Ampère, was a prosperous silk merchant and an educated man who encouraged his son's intellectual development. The family was comfortable, happy, intellectually alive. And then, the French Revolution came. In 1793, during the Reign of Terror, Lyon rose against the revolutionary government in Paris. The revolt was crushed, and in the aftermath, André-Marie's father was arrested and guillotined. André-Marie was 18 years old. By some accounts, the shock was so severe that he spent over a year in a state of near catatonia, unable to read, unable to work, barely able to function. He eventually recovered, threw himself into mathematics and science with a kind of desperate intensity, married, had a son, and then lost his wife to illness just a few years later. He was a man who had been broken and rebuilt, and there was a driven, almost haunted quality to everything he did afterward. So when Ampère heard about Ørsted's discovery, he didn't just find it interesting. He grabbed it, he tore into it. And the question he immediately asked was one that Ørsted hadn't explored. If a current-carrying wire creates a magnetic field, and that magnetic field can push a compass needle around, then what happens when you put two current-carrying wires next to each other? Does the magnetic field from one wire affect the other wire? The answer was yes, and Ampère demonstrated it with elegant clarity. Two parallel wires carrying current in the same direction attract each other. Two parallel wires carrying current in opposite directions repel each other. You don't need a compass needle. You don't need a magnet at all. Two ordinary wires carrying ordinary electric currents exert real, measurable mechanical forces on each other, pulling together or pushing apart, depending on the direction of current flow. This was a stunning result, and Ampère didn't just demonstrate it. He quantified it. He measured how the force depended on the current, on the distance between the wires, on the length of the wires. He was building a mathematical description of electromagnetism from scratch, and he was doing it at breathtaking speed, publishing paper after paper through the autumn and winter of 1820, driven by that intense, almost ferocious energy that characterized everything he did after the loss of his father and his wife. Meanwhile, other physicists were discovering the practical implications. If a current creates a magnetic field, and if winding the wire into a coil concentrates that field,
then you could make a magnet that you can turn on and off by controlling the current. William Sturgeon in England demonstrated the first practical electromagnet in 1825, a piece of iron wrapped in wire that became strongly magnetic when current flowed and lost its magnetism when the current stopped. This was an entirely new kind of magnet, one you could control. Within a few years, Joseph Henry in America was building electromagnets so powerful they could lift thousands of pounds of iron. The telegraph, which would revolutionize communication by the 1840s, depended directly on this principle. A current flowing through a wire at one end of a long line, creating a magnetic force at the other end, strong enough to click a lever and mark a paper tape. Electricity creating magnetism, on demand, across a distance. But stepping back to the pure science, what Ampere's work meant was profound. It meant that magnetism wasn't just linked to electricity. It was, in some deep sense, created by electricity. Whenever charges moved, whenever current flowed, a magnetic effect appeared around the moving charges. And that magnetic effect could push and pull on other currents, other moving charges, creating forces between wires that had no magnets anywhere near them. Ampère went further. He developed a mathematical framework to describe these forces, what we now call Ampere's law. And then he proposed something truly bold, a claim so radical that it took nearly a century to fully confirm. He suggested that all magnetism, everywhere, in every magnet that has ever existed, is caused by electric currents. Let that sink in for a second. Ampère was saying that a permanent magnet, a compass needle, a lodestone, the Earth itself, none of these contain some separate, independent, magnetic stuff. Instead, there must be tiny circular electric currents flowing inside the magnetic material, at a scale too small to see, and those microscopic currents are what create the magnetic effect. He called them molecular currents. Picture what he was imagining. Inside a bar magnet, at the level of individual atoms and molecules, tiny loops of electric current circulate endlessly. Each loop creates a tiny magnetic field, like a miniature electromagnet. In an unmagnetized piece of iron, these tiny loops are oriented randomly, their fields cancelling each other out, and the iron shows no magnetic properties. But when you magnetize the iron by stroking it with a lodestone or placing it in a strong magnetic field, the tiny loops align. They all start circulating in the same direction, and their individual fields add up, creating the macroscopic magnetic field that you can detect with a compass or feel with your hand as two magnets snap together. The magnet doesn't have magnetism as a separate property. The magnet has electric charges in motion, tiny currents at the atomic scale, and those currents are the sole and complete source of the magnetic effect. This turned out to be essentially correct, though the full explanation had to wait for quantum mechanics in the 20th century. The molecular currents that Ampère imagined are actually the orbital motion and spin of electrons within atoms. He had the right picture, just not the right mechanism. But the core insight, that magnetism is what electricity does when it moves, that there is no independent magnetic force, only the electromagnetic effect of charges in motion, that insight is one of the deepest truths in all of physics. Meanwhile, also in 1820, just months after Ørsted's discovery, two other French physicists, Jean-Baptiste Biot and Félix Savart, were doing their own careful measurements of the magnetic field around a current-carrying wire. They worked out the precise mathematical relationship between the strength of the current, the distance from the wire, and the strength and direction of the resulting magnetic field. The result, known as the Biot-Savart law, is still used today by engineers designing everything from MRI machines to electric motors. It tells you exactly how to calculate the magnetic field produced by any configuration of current-carrying wires. So by the end of 1820, just months after Ørsted's lecture in Copenhagen, the landscape of physics had transformed. The wall between the twins was cracking wide open. Electricity produces magnetism. Current creates magnetic fields. Two currents exert forces on each other, and maybe, just maybe, all magnetism everywhere is really just electricity in disguise. But notice what was still missing. Everything so far went in one direction. Electricity produces magnetism. Turn on a current and a compass needle moves. But what about the reverse? Can magnetism produce electricity? Can you start with a magnet and somehow get a current to flow? That was the obvious next question. Ørsted had shown one direction of the connection. Ampère had deepened it and extended it. But the other direction, magnetism creating electricity, remained an open problem. Ampère was thinking about it. Other physicists were thinking about it.
People tried experiments, looked for steady currents flowing near magnets, and found nothing. Take a moment here, if you like. Just breathe. We're deep into the story now, and the next part is, I think, the most beautiful, the most human. It involves a person whose life story is so improbable that if you put it in a novel, a reviewer would say it was too neat, too on the nose, too perfectly structured to be believable. And yet it's all true. The person who would eventually solve it, who would find the reverse link and complete the reunion of the twins, was working in a basement laboratory in London. He came from a background so unlikely, so improbable, that his story reads less like a biography and more like a fable. And the reason it took him 11 years to find the answer, the reason the reverse connection was even harder to spot than the forward one, contains one of the deepest and most counterintuitive insights in all of electromagnetism. Michael Faraday was born on September 22, 1791, in Newington Butts, a neighbourhood in what is now South London. His family was poor. His father, James Faraday, was a blacksmith who had moved to London from the north of England in search of work and who was frequently too ill to practice his trade. The family lived on the edge of real poverty, the kind where meals are uncertain and winter is something to be feared. Faraday later recalled that there were times when he and his siblings shared a single loaf of bread for an entire week. His formal education was minimal. He attended a local day school where he learned reading, writing, and basic arithmetic, and that was the end of his formal instruction. No algebra, no geometry, no Latin or Greek, certainly no science. By the standards of the academic world he would eventually dominate, he was essentially uneducated. At the age of 13, he was apprenticed to a bookbinder named George Rebow, who ran a shop on Blandford Street in London. The apprenticeship was for 7 years, and during that time, Faraday would learn the trade of binding and selling books. It was respectable work, a path to a stable, if modest, living. His family was grateful for the opportunity. And this is where the trajectory of his life changed, in one of those quiet pivots that seems almost too good to be fiction. Because the thing about being a bookbinder's apprentice is that you're surrounded by books. You handle them all day. You cut the pages, you stitch the spines, you press the covers. And if you're curious, if you have that particular hunger that some people are born with, you read them. And Faraday read everything. Science, history, philosophy, travel narratives, anything that passed through the shop. But two works in particular caught fire in his mind. One was an entry on electricity in the Encyclopaedia Britannica. The other was a popular science book called Conversations on Chemistry by Jane Marcet, written specifically to make science accessible to people without formal education. Faraday didn't just read these books, he started doing experiments. In the back of the bookbinding shop, using bottles and scraps of wood and wire, he built a crude electrostatic generator. He performed simple chemical experiments. He was teaching himself science from scratch, with no teacher, no laboratory, no funding, nothing but books and scraps, and an appetite for understanding that was, by all accounts, almost ferocious. In 1812, when Faraday was 20, a customer of the bookshop gave him tickets to a series of public lectures at the Royal Institution by Humphrey Davy, the most famous chemist in England. Faraday attended all 4 lectures.
He took notes, meticulous, beautiful, detailed notes. And then, because he was a bookbinder, he bound those notes into a handsome volume and sent it to Davy with a letter asking for a job. Any job. Anything that would let him work in science. Davy was impressed, though perhaps not entirely sure what to make of this earnest young man with no formal qualifications and a beautifully bound notebook of lecture summaries. He initially advised Faraday to stick with bookbinding, telling him that science was a harsh mistress that rewarded her servants poorly. But Davy also recognized talent when he saw it, and when a position as laboratory assistant opened up at the Royal Institution in 1813, after the previous assistant was fired for involvement in a brawl, Davy offered the job to Faraday. The salary was modest, a guinea a week, plus use of 2 rooms at the top of the building. The work involved cleaning equipment, maintaining apparatus, preparing demonstrations for lectures, and assisting senior scientists with their experiments. It was menial labor by academic standards, but for Faraday, it was paradise. He was inside the laboratory. He could watch experiments being performed. He could handle the instruments. He could ask questions and hear answers from working scientists. He was where the knowledge was being made. Faraday walked into one of the finest scientific laboratories in the world at the age of 21, and he never left. He would work at the Royal Institution for the rest of his life, rising from laboratory assistant to director, from anonymous helper to one of the most celebrated scientists in history. The bookbinder's apprentice, who read the Encyclopaedia Britannica by candlelight, would eventually turn down a knighthood and twice decline the presidency of the Royal Society.
He was offered a burial in Westminster Abbey, and his family declined that too, in accordance with his wishes. He wanted to be remembered for his work, not for his honours. Now, Faraday's early years at the Royal Institution were devoted to chemistry. He was superb at it. He discovered benzene. He liquefied chlorine for the first time. He did important work on steel alloys and the chemistry of gases. But the work that would make him immortal, the work that connects to everything we've been talking about, began in the early 1820s, when Faraday turned his attention to the relationship between electricity and magnetism. Like everyone else in physics, Faraday knew about Ørsted's discovery. He knew that an electric current creates a magnetic field. He knew about Ampere's work on the forces between current-carrying wires. And in 1821, just a year after Ørsted's discovery, Faraday made his own first contribution to electromagnetism, and it was a remarkable one.
He built the first electric motor. It was a simple device, almost primitive. A wire dangled vertically into a pool of mercury with a permanent magnet standing upright in the middle. When Faraday sent a current through the wire, the magnetic field from the current interacted with the field from the magnet, and the wire began to rotate around the magnet in a continuous circle. A current-carrying wire spinning endlessly around a magnet. Continuous rotary motion produced by electromagnetic force, the principle that would eventually power every electric motor on the planet, from the tiny vibration motor in your phone to the enormous motors that drive industrial machinery. This early success established Faraday as a major figure in electromagnetic research, but it also created a painful complication. Humphrey Davy, his mentor and patron, accused Faraday of stealing the idea from another scientist, Wollaston, who had discussed the possibility of electromagnetic rotation. The accusation was almost certainly unfair. Faraday's approach was distinctly different from Wollaston's suggestion. but it damaged the relationship between Faraday and Davy and cast a shadow over what should have been a triumph. Davy even opposed Faraday's election to the Royal Society in 1824. Faraday was elected anyway, but the episode left scars, and then Faraday was consumed by the reverse question. If electricity creates magnetism, can magnetism create electricity? He had an advantage that the continental physicists, the French and German mathematicians who dominated the field, didn't fully appreciate. Faraday thought in pictures. He had essentially no mathematical training. He couldn't read the equations that Ampère and Biot and Savart were writing. The elegant formalisms of French mathematical physics were a closed book to him. But he had an extraordinary ability to visualize physical processes, to imagine what was happening in the space around a magnet or a wire, to see patterns and structures where others saw only empty air. And this visual, intuitive approach led Faraday to develop one of the most powerful and important concepts in the entire history of physics: the concept of the field. And to understand why this matters so much, we need to pause and think carefully about what was being claimed. Because the field concept is so familiar to us now, so thoroughly embedded in how we teach and think about physics, that it's easy to forget how radical it was when Faraday first proposed it. Before Faraday, the standard way of thinking about electric and magnetic forces was action at a distance. You have two charges, or two magnets. They push or pull on each other across empty space. The force just reaches from one to the other somehow. Nobody worries too much about the mechanism.
Newton's gravity worked the same way. The sun pulls the earth pulls the sun. The force leaps across 93 million miles of void, and nobody asks how. Faraday found this deeply unsatisfying. When he sprinkled iron filings on a piece of paper held over a magnet and saw them arrange themselves into those beautiful curving patterns, arcing from pole to pole in sweeping lines, he didn't see a mathematical abstraction. He saw something real. He saw lines of force, physical structures filling the space around the magnet. The space wasn't empty. It was full of something, a condition, a state of readiness, a field that permeated the entire region and told objects how to move. Most of the mathematically trained physicists on the continent thought this was naive. They had their equations, their inverse square laws, their elegant action at a distance formulations, and they didn't need to imagine invisible lines filling up space.
Faraday was just a self-taught experimenter who didn't know enough mathematics to think properly. That was the attitude. Some of them said it more politely than others, but that was the gist. They were wrong. Faraday was right. And the depth of his rightness is still being appreciated today. Think about what Faraday was claiming. He was saying that when you place a charge in empty space, the space itself changes. It acquires a property it didn't have before. At every point surrounding that charge, the space now contains information, a direction and a magnitude. If you were to place a second charge at that point, it would feel a force, and the direction and strength of that force are encoded in the field at that location. The charge creates the field. The field fills all of space, and the field acts on other charges. The field is the intermediary, the messenger, the medium through which the force is communicated. This is a fundamentally different picture from action at a distance. In the old picture, two charges reach across empty space and grab each other. In Faraday's picture, each charge creates a field in the space around it, and the other charge responds to the field at its own location. The field exists whether or not there's a second charge there to feel it. The field is real. It has energy. It has structure. It is, in a very concrete sense, a physical thing, even though you can't see it or touch it. The iron filings made this vivid. When you sprinkle iron filings on a sheet of paper above a magnet, each tiny piece of iron becomes a little magnet itself, aligning with the field at its location. The pattern they form, those sweeping curves arcing from pole to pole, is a map of the field, a photograph of the invisible. And the patterns are not random, they're orderly, structured, and beautiful. And they reveal something about the geometry of the field that equations alone might not convey. The field is dense and intense near the poles of the magnet, where the lines crowd together. It's weaker further away, where the lines spread apart. It curves, it flows, it has a topology, a shape, a character. Faraday saw all of this, and he trusted what he saw. He trusted his physical intuition over the mathematical conventions of the day. And the field concept would eventually become the central organizing idea of all modern physics. Every force we know about, every interaction, every particle, is now understood in terms of fields. Quantum field theory, the deepest framework we currently have for understanding the subatomic world, is built entirely on the idea that fields are fundamental and particles are excitations of those fields. The electron is a ripple in the electron field. The photon is a ripple in the electromagnetic field. Faraday couldn't have known any of this, but he planted the seed. He saw it first.
He saw it because he couldn't do the math, because he had to think in physical, spatial, visual terms. And that turned out to be exactly what the problem required. But we're getting ahead of ourselves. Faraday's field concept was visionary, but what he needed right now was the answer to his burning question. Can magnetism create electricity? And for over a decade, he tried to find it, and he failed. He placed a wire near a magnet and looked for a current flowing through the wire. Nothing. He wrapped a coil of wire around a magnet and connected it to a galvanometer, a sensitive instrument for detecting small currents, and watched the needle. Nothing. The magnet just sat there. The wire just sat there. No current flowed. And the reason it took so long, the reason the reverse connection eluded him for 11 years of persistent effort, reveals something beautiful and deep about the nature of electromagnetism. Something nobody expected.
Something that, once understood, would transform our understanding of how the universe works at the most fundamental level. Here's what was going on. Faraday tried, again and again, to produce a current from a magnet. He placed powerful permanent magnets next to wires connected to his most sensitive galvanometers. He waited. He watched the needle. Nothing happened. He left the magnet next to the wire for hours, sometimes overnight. Still nothing. He wrapped coils of wire around magnets, hundreds of turns, thinking that more wire would amplify any tiny effect. He connected the coils to galvanometers. The needle sat dead still. The problem, which he couldn't have known at the time, was in his assumption. He was looking for a steady current. He expected that if you put a wire near a magnet, a current would flow continuously, the same way current flows continuously when you connect a wire to a battery. He expected symmetry. Electricity produces a steady magnetic field. Therefore, magnetism should produce a steady electric current. That seemed like the natural mirror image. But it was wrong. And the word wrong, in this case, contains one of the most profound surprises in the history of physics. The breakthrough came on August 29, 1831. Faraday had built a device consisting of an iron ring, about 6 inches in diameter, with 2 separate coils of wire wound around it on opposite sides. One coil was connected to a battery. The other was connected to a galvanometer. His idea was that if electricity in the first coil created magnetism, and that magnetism traveled through the iron ring to the second coil, maybe it would induce electricity in the second coil. So he connected the battery, sending current through the first coil, and the galvanometer needle on the second coil twitched. It jumped, briefly, sharply, to one side, and then settled back to 0. Faraday stared at it. He waited. The battery was still connected.
Current was still flowing through the first coil. The magnetic field through the iron ring was now steady and strong, but the galvanometer read 0, no current in the second coil. Then he disconnected the battery, and the galvanometer needle jumped again, this time in the opposite direction. A quick, sharp deflection, and then back to 0. Faraday's laboratory notebook for that day, which still exists and can be seen at the Royal Institution, records the result with characteristic brevity. But you can sense, even in the careful handwriting, a surge of excitement. Because he understood what he was seeing. The current in the second coil appeared only at the moment of change. When the battery was connected, when the magnetic field through the ring was growing, a momentary current appeared. As soon as the field stabilized, even though it was now strong and steady, the current disappeared.
And when the battery was disconnected, when the field was collapsing, the current appeared again briefly, flowing in the other direction. Faraday had found the reverse connection. Magnetism can create electricity, but only changing magnetism. A static magnetic field, no matter how strong, sitting next to a wire does nothing. Move the magnet, push it toward the wire or pull it away, and current flows. Stop moving it, and the current stops. The change is everything. The variation in time is what matters. This is Faraday's law of electromagnetic induction, and the asymmetry it reveals is profound. A steady current creates a steady magnetic field, but a steady magnetic field does not create a steady current. To get electricity from magnetism, you need the magnetic field to be changing, growing, shrinking, moving, varying. The symmetry between the twins is not perfect.
And that imperfection, that subtle asymmetry, turns out to be the key to understanding electromagnetic waves, light, radio, everything. But we'll get to that. Let that settle for a moment. The static magnetic field, sitting there patiently, does nothing to the wire. You can wait a year, a century, a millennium, no current. But move the magnet, change the field, let the magnetic flux through the coil increase or decrease, and suddenly electrons flow. The universe only responds to change, to variation, to motion. The deeper you go into electromagnetism, the more you find this principle echoing. Static situations are stable. Change creates new phenomena. The whole theory is, in a sense, a theory of how change propagates through space. But we're getting ahead of ourselves. Faraday spent the rest of 1831 exploring his discovery with the thoroughness of a man who knows he's found gold. He showed that you could induce a current by simply sliding a magnet in and out of a coil of wire. Push the magnet in, current flows one way. Pull it out, current flows the other way. Hold it still, no current. He showed that spinning a copper disc between the poles of a magnet produced a continuous current, the first electric generator, the first dynamo. He showed that the voltage you induced depended on how fast you changed the magnetic field and how many loops of wire you used. More loops, more voltage. Faster change, more voltage. And here's something worth sitting with. Every single one of those rules, more loops gives more voltage, faster change gives more voltage. The induced current opposes the change that creates it. Every one of them was discovered experimentally by a man with no mathematical training, working alone in a basement laboratory, guided by physical intuition and an almost superhuman ability to design revealing experiments. Faraday couldn't write the equation for induction that now bears his name, but he discovered every fact that the equation encodes. The mathematics was added later by others. The physics was his. This principle, electromagnetic induction, is how virtually all the electricity in the world is generated. Right now, Tonight, the electricity powering whatever device you're listening to this on was almost certainly produced by Faraday's principle. Somewhere, a turbine is spinning, driven by steam from burning fuel or from nuclear fission, or by falling water, or by wind. That spinning turbine is rotating a magnetic field inside coils of wire. The changing magnetic field is pushing electrons through those wires, creating the current that flows through the grid to your home. The basic mechanism is exactly what Faraday demonstrated in 1831 with his iron ring and his galvanometer. The scale is incomparably larger. The engineering is vastly more sophisticated, but the principle is identical. And there's another beautiful consequence of induction that Faraday noticed, and that was later formalized by a Russian-born physicist named Heinrich Lentz. When you induce a current by changing a magnetic field, the induced current itself creates its own magnetic field, and that secondary field always opposes the change that created it. Always. If you push a magnet toward a coil, the induced current creates a field that pushes back against the magnet, resisting its approach. If you pull the magnet away, the induced current creates a field that tries to hold it in place. Nature resists the change. It fights back against whatever is altering the magnetic field. This is Lenz's law, and it's really a consequence of conservation of energy.
If the induced current helped the change instead of opposing it, you'd get a runaway effect. The current would strengthen the field change, which would increase the current, which would strengthen the change further, and you'd be creating energy from nothing. That can't happen. Energy can't come from nowhere. So the universe pushes back. The induced effect always opposes the change that caused it. If you've ever seen a demonstration where someone drops a strong magnet through a copper tube, you've seen Lenz's law in action. The magnet falls slowly, almost lazily, as if it were sinking through honey instead of falling through air. The copper tube is not magnetic. A compass needle wouldn't notice it at all. But the moving magnet's changing field induces currents in the copper, and those currents create their own magnetic fields that oppose the magnet's motion, slowing it down. No friction, no contact. Just the invisible hand of electromagnetic induction reaching up from the copper to break the falling magnet. The same principle is used in the braking systems of high-speed trains and some roller coasters. Eddy current brakes, they're called. No pads, no wear, no squeal of metal on metal. Just a magnet and a conductor, and the quiet, elegant resistance of Lenz's law. In 1845, Faraday made another discovery that stunned the scientific world and brought yet another phenomenon into the electromagnetic family. He showed that a strong magnetic field could rotate the plane of polarized light. Polarized light is light whose waves all oscillate in the same direction, and Faraday demonstrated that when you shine polarized light through a piece of glass sitting inside a powerful magnetic field, the plane of polarization twists. The angle of rotation depends on the strength of the field and the distance the light travels through it. This effect, now called Faraday rotation, was the first experimental evidence that light and electromagnetism were somehow connected. Light, that most ancient and mysterious of phenomena, was tangled up with the same forces that made compass needles point north, and iron filings arrange themselves into patterns. Faraday suspected, and he wrote about it in his notebooks with a kind of breathless excitement that's unusual for him, that light itself might be a vibration of those very lines of force he had been imagining for decades. An electromagnetic disturbance, rippling through space. He didn't have the mathematics to prove it, but someone else did. By the early 1830s, the reunion of the twins was well underway. Ørsted had shown that electricity creates magnetism. Faraday had shown that changing magnetism creates electricity. The two forces were intertwined, each capable of generating the other under the right conditions. But the picture was still incomplete. The mathematical framework was patchwork, a collection of separate laws: Coulomb's law, Ampere's law, Faraday's law, the Biot-Savart law, each describing a piece of the puzzle, but not fitting together into a single, unified picture. And the details that were still missing, the gaps that still needed filling, concealed one final surprise. The biggest one. The one that would reveal that electricity and magnetism are not just related, not just connected, not just two aspects of the same force. They are, in a very precise and beautiful sense, the stuff that light is made of. And the man who would see that, who would take Faraday's physical intuition and translate it into the language of mathematics, and in doing so discover the nature of light, was about to enter the story. He was born in Edinburgh in 1831, the very same year Faraday discovered induction, which is a coincidence so poetic it almost seems deliberate. His name was James Clerk Maxwell, and he was, by any reasonable measure, one of the greatest physicists who has ever lived. James Clerk Maxwell grew up on his family's estate at Glenlair in the rolling countryside of Galloway in southwestern Scotland. His father, John Clerk Maxwell, was a devoted but somewhat eccentric man who designed unusual clothing for his son, including a pair of shoes with square toes and a tunic with a frilly collar that would have been unremarkable in an earlier era, but looked distinctly odd in the 1830s. When young James was sent to the Edinburgh Academy at the age of 10, the other boys took one look at his homemade outfits and immediately dubbed him Dafty. He was bullied, as children in strange clothes tend to be, but he endured it with a stubbornness that his classmates eventually came to respect, partly because they realized that the odd-looking boy was, in intellectual terms, operating on an entirely different level. At the age of 14, Maxwell wrote his first mathematical paper on the geometry of oval curves, and it was presented to the Royal Society of Edinburgh. The paper was read aloud by a professor because the society felt it would be improper for a schoolboy to present in person. 14 years old, and his mathematics was good enough for the Royal Society. The other boys stopped calling him Dafty. His mother, Frances, had died of cancer when he was 8, and that loss marked him deeply. He grew up quiet, thoughtful, almost maddeningly careful in his reasoning, the kind of person who would turn a problem over in his mind for weeks or months before committing anything to paper, and then produce something so precise and so beautiful that it took the rest of the scientific community years to fully appreciate what he'd done. Maxwell went to the University of Edinburgh, and then to Cambridge, where he studied at Trinity College and graduated as second wrangler in the mathematical tripos, the most demanding mathematics examination in the English-speaking world. Second wrangler meant second highest score. Only one person did better. He held academic positions at Marischal College in Aberdeen, then at King's College London, and finally returned to Cambridge as the first Cavendish Professor of Physics in 1871, where he designed and oversaw the construction of the Cavendish Laboratory, which would become one of the most important physics research centres in the world. Throughout all of this, Maxwell remained a deeply private, quietly religious man, devoted to his wife Catherine and to his work. He published on an astonishing range of subjects, making foundational contributions to the theory of colour vision, the kinetic theory of gases, thermodynamics, and the mathematical analysis of Saturn's rings, in addition to his work on electromagnetism. He was, in the judgment of many physicists, the most important physicist between Newton and Einstein, and there's a good case to be made that his work was more transformative than either of theirs, though such rankings are ultimately a matter of taste. But his greatest work, the work that concerns us tonight, was done during the late 1850s and 1860s, when he turned his attention to the problem that Faraday had spent decades wrestling with: the nature of electric and magnetic fields. Here's what Maxwell saw, and what nobody else had seen clearly enough to act on. By the 1850s, there was an enormous amount of experimental knowledge about electricity and magnetism.
Coulomb had measured the force laws. Ampère had described how currents interact. Faraday had discovered induction. Biot and Savart had quantified the magnetic field around a wire. There were dozens of known relationships, hundreds of experimental results. But there was no unified mathematical framework tying it all together. The knowledge was like 1,000 puzzle pieces scattered across a table, with no picture on the box to show what the completed puzzle should look like. Maxwell decided to build the picture. He started by doing something that most physicists at the time considered slightly eccentric. He took Faraday's lines of force seriously, not as a metaphor, not as a convenient way to visualize something, but as a mathematical reality. Where most physicists thought in terms of action at a distance, charges reaching across empty space to push and pull each other, Maxwell adopted Faraday's view that the space itself was doing something. The fields were real, they filled space, they carried energy.
They had their own dynamics. In his early papers, Maxwell used beautiful analogies to develop his mathematics. His first major paper on the subject, published in 1855 and 1856, was called On Faraday's Lines of Force. In it, he compared electric field lines to the flow of an incompressible fluid through a porous medium. He didn't mean that electric fields literally were fluid flows. He meant that the mathematics were analogous, and by borrowing the well-developed tools of fluid dynamics, he could describe the behavior of electromagnetic fields with precision. It was a brilliant strategy, using the known mathematics of one domain to illuminate unknown physics in another, and it produced results that were both elegant and testable. Think about what Maxwell was doing here, because it captures something essential about how theoretical physics works. Faraday had the right physical picture, but lacked the mathematical language to express it.
The continental physicists had sophisticated mathematics, but were committed to the wrong physical picture: action at a distance. Maxwell bridged the gap. He took the right physics from Faraday and married it to the right mathematics, and the result was something neither could have achieved alone. His second major paper, On Physical Lines of Force, came in 1861 and 1862. And this is where things get truly extraordinary. Maxwell tried to build a mechanical model of the electromagnetic field. He imagined space filled with tiny rotating vortices, like microscopic spinning cells, with idle wheel particles between them to allow adjacent vortices to rotate in the same direction without grinding against each other. It was an elaborate, almost Rube Goldberg-like contraption, a mechanical clockwork filling all of space. And honestly, the model itself was wrong. Space is not full of tiny gears. Nobody believed that, and Maxwell himself likely didn't either. But the equations he derived from this mechanical model turned out to be profoundly, lastingly, almost miraculously correct. Sometimes in science, you can arrive at the right destination by taking a wrong road, and Maxwell's vortex model is one of the most famous examples of this. And here's where the thunderbolt hits. As Maxwell was working through his equations, checking them for internal consistency, making sure all the mathematical pieces fit together, he noticed a problem. The existing laws, the ones established by Ampère and Faraday and Gauss, were almost mathematically consistent. Almost. But there was a gap. A small inconsistency. A place where the equations didn't quite balance. Specifically, Ampère's law, as it was understood at the time, said that magnetic fields are created by electric currents, by charges physically flowing through wires. And that was true. But Maxwell realized that if this were the complete story, the equations would predict violations of conservation of charge, which was a bedrock principle. Charge doesn't just appear or disappear. Something was missing. So Maxwell proposed a fix.
And this fix, this one small addition, this single term added to a single equation, would turn out to be one of the most consequential ideas in the entire history of physics. He added a term to Ampere's law. He said, "What if a changing electric field also creates a magnetic field, even when there's no actual current flowing?" He called this the displacement current. The name is a bit misleading because it's not really a current in the usual sense, not electrons moving through a wire. It's the idea that when an electric field is changing in time, the change itself acts as a source of magnetism, just as a real flowing current does. Think about the symmetry of this. Faraday had shown that a changing magnetic field creates an electric field.
That's induction. That's generators and transformers and the entire electrical grid. Maxwell was now proposing the mirror image. A changing electric field creates a magnetic field. Each field, when it changes, gives birth to the other. And then Maxwell did what Maxwell did best. He sat down with his completed set of equations, the ones with the displacement current term added, and he asked, what happens if you have a region of space with no charges and no currents, just fields? Can the fields sustain themselves? Can a changing electric field create a magnetic field, and can that changing magnetic field create an electric field, back and forth, each one generating the other, propagating outward through empty space as a self-sustaining wave? He worked through the mathematics. The calculation was involved, requiring careful manipulation of partial differential equations, but the logic was clear and the steps were rigorous. And the answer was yes. The equations predicted the existence of electromagnetic waves, self-sustaining oscillations of coupled electric and magnetic fields that would propagate through empty space at a specific, calculable speed. The wave works like this. Imagine a region of space where, for some reason, the electric field is changing rapidly. According to the fourth equation, Ampere's law with the displacement current, that changing electric field creates a magnetic field in the neighboring region of space. But now, that magnetic field is also changing because it just appeared where there was none before. And according to the third equation, Faraday's law, that changing magnetic field creates an electric field in the next neighboring region. And that electric field is changing too, so it creates more magnetic field, and so on, and so on. The disturbance propagates outward through space, each field giving birth to the other, like a wave passing through water, except that no water is needed, no medium of any kind. The fields carry themselves. And then he calculated the speed at which this self-propagating disturbance would travel. The speed depended on two numbers, two constants that had been measured in the laboratory through experiments on electric and magnetic forces. The permittivity of free space, which tells you how strong the electric force is between charges in a vacuum, and the permeability of free space, which tells you how strong the magnetic force is between currents in a vacuum. Both of these numbers had been carefully measured. They had nothing to do with light. As far as anyone knew, they were just constants that described the strength of electrical and magnetic interactions. Maxwell combined them, according to the formula his equations demanded, took the square root, inverted the result, and got a number. And that number was approximately 193,000 miles per second. He must have stared at it. He must have checked his arithmetic. He must have gone back through the derivation step by step, looking for an error. Because the measured speed of light at the time was approximately 195,000 miles per second. 193 versus 195. The agreement was within the experimental uncertainty of the measurements. It was too close to be coincidence. Way too close. It was too precise to be an accident. And Maxwell wrote, in one of the most understated and momentous sentences in the history of science, "We can scarcely avoid the inference that light consists in the transverse undulations of the same medium which is the cause of electric and magnetic phenomena. Light is an electromagnetic wave, the thing that lets you see the world, the thing that warms your skin when you step into sunlight, the thing that travels from stars across billions of miles of empty space to reach your eyes. It is made of electric and magnetic fields oscillating together, leapfrogging through the vacuum, each one giving birth to the other, exactly as Maxwell's equations predicted. Let that settle for a moment, because this is, without exaggeration, one of the greatest unifications in the history of human thought. For thousands of years, light was one mystery, magnetism was another, electricity was a third. Three separate enigmas, studied by different people using different tools in different traditions. And Maxwell showed, on a few pages of mathematics, that they are all the same thing. One phenomenon, one set of laws, one unified force that we now call electromagnetism. The twins were not just reunited, they were revealed to be, and to have always been, a single entity. And their reunion revealed the nature of something that had been the deepest mystery of all. Maxwell published his definitive treatment in 1865 in a paper titled A Dynamical Theory of the Electromagnetic Field, and expanded it in his 1873 treatise. The final form of his equations, what we now call Maxwell's equations, consists of four compact mathematical statements that describe all of classical electromagnetism. Every electric field, every magnetic field, every light wave, every radio signal, every X-ray, every microwave warming your dinner, all of it flows from those four equations. Let me describe them in words, because even without the math, they're beautiful. And even if the names and technical details fade from memory by tomorrow, the shape of these ideas, the elegance of how they fit together, is something worth carrying with you. The first equation is usually attributed to Carl Friedrich Gauss, and it says that electric charges are sources of electric field. If you have a positive charge, field lines radiate outward from it in all directions, like rays of light from a tiny sun. If you have a negative charge, field lines converge inward toward it, like water flowing into a drain. The total amount of electric field passing outward through any closed surface, any imaginary bubble you draw around a region of space, is exactly proportional to the total charge enclosed inside that bubble. More charge inside means more field passing through. Zero charge inside means the total field passing through is zero, even if fields from external charges are passing through in one side and out the other. This is Gauss's law, and it encodes everything about how electric charges create electric fields. It's the mathematical expression of the fact that charges are the sources and sinks of the electric field, the places where field lines begin and end. The second equation says that there are no magnetic monopoles, no isolated north or south poles. Every magnetic field line that leaves a surface must also enter it somewhere. Magnetic field lines always form closed loops. You can never cut a magnet in half and get just a north end without a south end. Remember Petrus Peregrinus, back in 1269, sitting outside that besieged city with his lodestone, discovering that breaking a magnet always gives you two complete magnets. Maxwell's second equation is the mathematical expression of exactly that observation, elevated from a curious fact about rocks to a fundamental law of nature. The third equation is Faraday's law.
A changing magnetic field creates a curling electric field. This is induction. This is generators and transformers and the entire electrical power system. The fourth equation is Ampere's law with Maxwell's addition. Electric currents and changing electric fields both create curling magnetic fields. This is the equation Maxwell fixed, the one that completed the symmetry and made electromagnetic waves possible. 4 equations, and from them you can derive the behavior of everything from a compass needle to a lightning bolt to the light from a distant galaxy. Maxwell didn't live to see the full vindication of his work. He died on November 5, 1879, at the age of 48 of abdominal cancer, the same disease that had killed his mother at almost the same age. In the weeks before his death, attended by his wife Catherine, he remained characteristically calm and composed. He told his doctor, "I have been thinking about the door into the next world. The grand thing is that it opens the other way, and we don't have to strain to get through." He died, knowing his theory was mathematically beautiful and self-consistent. He died believing, with good reason, that electromagnetic waves other than light must exist. But nobody had yet built a device to produce and detect them in a laboratory. Nobody had yet proven, experimentally, that you could generate waves made of oscillating electric and magnetic fields and catch them across a room. The theory predicted their existence, the math was watertight, but the experimental proof was missing. That proof would come within a decade, and it would come from a physicist working in a modest laboratory in Germany, in conditions that make you appreciate how much of experimental physics depends on patience, darkness, and very good eyesight. Heinrich Hertz was born in 1857 in Hamburg, Germany, into a prosperous and cultured family. His father was a lawyer who later became a senator, and the household valued education, literature, and music. Young Heinrich showed early talent in both the sciences and the crafts, building instruments in a workshop at home, and he eventually studied physics under Hermann von Helmholtz in Berlin, one of the grand old men of German science. Helmholtz recognized Hertz's gifts immediately and encouraged him to tackle the biggest open question in electromagnetic theory: whether Maxwell's predicted waves actually existed as physical phenomena. Hertz didn't rush at the problem. He spent years building his knowledge and his skills, taking a position at the University of Kiel and then moving to the Technische Hochschule in Karlsruhe, where the laboratory facilities gave him the space and equipment he needed. By the mid-1880s, he was ready. His approach was direct and elegant. Maxwell's equations said that any rapidly changing electric current should radiate electromagnetic waves into the surrounding space. So Hertz built a device that produced exactly that: a rapid, violent change in current. His transmitter was essentially a spark gap. 2 metal rods positioned with a small gap between them connected to an induction coil that would build up voltage until a spark jumped across. That spark, that brief, intense burst of current, was exactly the kind of rapidly oscillating electromagnetic disturbance that Maxwell's equations said should radiate energy outward as waves. The question was, could Hertz catch those waves? His detector was almost absurdly simple: a loop of wire with its own tiny gap positioned across the room from the transmitter. The idea was that if electromagnetic waves were really spreading outward from the spark, they would induce a small voltage in the loop, enough perhaps to cause a tiny, barely visible spark to jump across the detector's gap. Picture the scene. Hertz is working in a darkened laboratory in Karlsruhe. The windows are covered, the lights are out. He needs absolute darkness because the sparks he's looking for in the detector are so faint, so minute, that he needs his eyes fully dark adapted to have any hope of seeing them. Even the faint glow of a street lamp leaking through a crack in the curtains would wash them out. He fires the transmitter. The main spark cracks across the gap with a flash and a sharp snap.
momentarily illuminating the room with a violent blue-white light. And then, darkness again. And in that darkness, Hertz peers, literally peers with his dark adapted eyes across the room at the little loop of wire sitting on a stand, looking for the faintest possible glimmer, a spark jumping across a fraction of a millimeter in the detector's tiny gap. And he sees it. A minute, pale, almost ghostly spark, barely there, but real and unmistakable and repeatable. That moment, in 1887, is one of the great experimental confirmations in the history of science. Maxwell had predicted, purely from mathematics, that electromagnetic waves should exist. And here was Hertz, in a darkened lab in Karlsruhe, watching them arrive. He didn't stop there. He measured the waves. He reflected them off metal sheets and created standing wave patterns, the same way you can create standing waves on a vibrating guitar string. He calculated the wavelength, multiplied by the frequency he knew from his transmitter, and got the speed. And the speed was the speed of light. Exactly as Maxwell had predicted, he showed that his waves could be reflected off flat metal surfaces, just like light reflecting off a mirror. He showed they could be refracted, bent, when they passed through a prism made of pitch, just like light bending through glass. He showed they could be polarized, filtered, so that the electric field oscillated in only one direction, just like light passing through a polarizing filter. In every measurable way, his waves behaved identically to light. The only difference was scale. Light waves have wavelengths measured in hundreds of nanometers, far too small to see individually. Hertz's waves had wavelengths measured in meters, large enough to wrap around furniture. But the physics governing them was the same. The equations describing them were the same. They traveled at the same speed. Hertz also noticed something during his experiments that he didn't fully understand at the time, but that would eventually open yet another chapter in physics. He observed that the spark in his detector was slightly easier to see when ultraviolet light from the transmitter's spark was allowed to fall on the detector. Shielding the detector from the UV light made the sparks harder to produce. This was the photoelectric effect, the phenomenon that Einstein would later explain using the quantum theory of light, earning him the Nobel Prize in 1921. Hertz noticed it, recorded it, and moved on. He had bigger things on his plate.
But it's a lovely irony that in the very act of confirming Maxwell's classical theory of electromagnetic waves, Hertz stumbled onto the first hint of the quantum revolution that would eventually supersede it. Maxwell had been right. Light is an electromagnetic wave, and there is a whole spectrum of electromagnetic radiation out there, from radio waves miles long to gamma rays smaller than an atom. All of it made of the same interlocking dance of electric and magnetic fields. All of it traveling at the same speed. All of it described by the same 4 equations. Now, there's a wonderful irony in Hertz's story. When people asked him what practical use these electromagnetic waves might have, he reportedly said, "None whatsoever." He saw his work as pure science, a confirmation of a beautiful theory, nothing more. He couldn't imagine any practical application for invisible waves radiating from a spark gap in a laboratory.
Hertz died young, in 1894, at the age of 36, from a rare disease that attacked his blood vessels. He didn't live to see what his waves would become. And what they became is almost beyond imagining. Within a decade of his experiments, Guglielmo Marconi was sending wireless telegraph signals across the English Channel. By 1901, Marconi sent a signal across the Atlantic Ocean, from Cornwall to Newfoundland, electromagnetic waves arcing over the curve of the Earth. Within a few more years, radio broadcasting was born, and suddenly a voice in one city could be heard in 1 million homes simultaneously, carried on the oscillating electric and magnetic fields that Hertz had first detected in his darkened laboratory. Television followed in the 1920s and 30s. Radar followed in time for the Second World War, using reflected electromagnetic waves to detect aircraft at distances that would have seemed magical a generation earlier. Satellite communication, microwave ovens, Wi-Fi, cell phones, GPS, Bluetooth. Every single technology that involves transmitting information or energy without wires, from the walkie-talkie to the smartphone in your pocket, traces directly back to Hertz's little spark in a darkened room, and to the 4 equations Maxwell wrote on a few pages of paper, and to Faraday's lines of force, and to Ørsted's compass needle twitching on a table in Copenhagen, and ultimately, all the way back, to a Greek philosopher 26 centuries ago who rubbed a piece of golden stone against a scrap of fur and watched, amazed, as straw jumped toward it through empty air. The twins, separated for 2,000 years, were fully and completely reunited. And their reunion had revealed along the way the nature of the most fundamental thing in the human experience of the world: light. And the reunion went even deeper than Maxwell and Hertz realized. 20 years after Hertz's experiment, a patent clerk in Bern named Albert Einstein would look at Maxwell's equations and notice something that nobody else had fully appreciated. If you're moving relative to a wire carrying a current, what you see as a magnetic force, someone standing still sees as an electric force. The two forces aren't just connected. They're different views of the same thing. The way the front and the side of a building are different views of the same structure. Which one you see depends on where you're standing, or in this case, how fast you're moving. Einstein's theory of special relativity, the one that gave us E equals mc squared, grew directly out of this insight. Its original title was On the Electrodynamics of Moving Bodies. The twins, it turned out, weren't just siblings. They were the same person, seen from different angles. But that's a longer story for another night. Now, I want to circle back to something we touched on earlier, because it matters deeply for understanding what electric charges and fields actually are, and because it ties together the entire story we've been walking through. When we talk about the electric field created by a charge, we're talking about something that exists at every point in space around that charge. Not just at the locations where there happens to be another charge to feel the force. The field is there whether anyone is there to notice it or not. It fills the room you're lying in right now. It extends outward in every direction, growing weaker with distance following the inverse square law that Coulomb measured with his torsion balance, but never reaching exactly zero. In principle, the field from every charge in the universe extends to every other point in the universe. It just gets unimaginably faint over large distances, and when multiple charges are present, their fields simply add together. The field at any point in space is the vector sum of the contributions from every charge in the universe. This is called the superposition principle, and it's one of those ideas that sounds almost too simple to be deep, but turns out to be enormously powerful. It means you can analyze any complex arrangement of charges by breaking it into individual charges, calculating each one's field, and adding them up. 2 charges, 1,000 charges, 10 trillion charges. The method is the same. The linearity of this addition is what makes electromagnetic theory practical, what makes it possible for engineers to design circuits and antennas and motors and everything else in the electrical world. Without superposition, the mathematics would be hopelessly intractable. With it, the field from even the most complicated charge distribution can be computed, one piece at a time. When Faraday imagined his lines of force, when he looked at iron filings arranging themselves in patterns around a magnet, he was seeing something that most people dismissed as a visualization aid, a teaching tool.
a way to picture something that didn't have a physical reality of its own. The real physics, the serious physicists said, was in the equations, in the action at a distance formulations, in the forces between charges calculated from Coulomb's law. But Faraday was right, and they were wrong. The field is real. It is not a mathematical convenience. It is not a shorthand for forces between particles. The electric field and the magnetic field are physical entities that exist in space, carry energy, exert forces, and propagate as waves. When Maxwell showed that electromagnetic waves exist, he was showing that fields can break free from the charges and currents that created them and travel through empty space on their own, carrying energy from one place to another. A light wave doesn't need a charge at its destination to pull it forward. It propagates by its own internal dynamics, each changing electric field giving birth to a magnetic field, each changing magnetic field giving birth to an electric field, leapfrogging forward at 186,000 miles per second, independently of any source or any receiver. The field is as real as the charge. In fact, in modern physics, the field is arguably more fundamental than the charge. Charges are understood as excitations of quantum fields, localized disturbances in underlying field structures that permeate all of space. The electron is a ripple in the electron field. The photon is a ripple in the electromagnetic field. The field came first. The particle is what the field does when it gets excited. Faraday, the bookbinder's apprentice who couldn't read an equation, saw this more clearly than almost anyone. He saw that the space around a charge is not empty. It is structured, dynamic, full of tension and direction and energy. He saw that when you bring two charges together, they don't reach across empty space and grab each other. Instead, each charge creates a field in the space around it, and the other charge responds to the field at its own location. The field is the intermediary. The field is the messenger. The field is the thing. This is what an electric field is, in the deepest sense we currently understand. It is a condition of space itself, a property that every point in the universe possesses, telling any charge that happens to be there which way to move and how hard. And the pattern of the field, the way it points and how strongly, encodes everything about the arrangement of charges that created it. And the electric charges themselves, the plus and minus that Franklin named, the things that attract and repel and flow through wires and accumulate on surfaces, what are they? At the most fundamental level, we still don't fully know. Charge is what physicists call an intrinsic property. Like mass, it's a fundamental attribute that particles simply have. You can't explain it in terms of something simpler. You can't open up an electron and find the little nugget of chargeness inside. We know how it behaves. We know it's conserved. Franklin showed us that. We know it's quantized. It comes in fixed, indivisible units. We know it follows precise mathematical laws. Coulomb showed us that. But what it actually is, why some particles have it and others don't, why the electron's charge is exactly the value it is and not some other number, those questions remain open. And there's something beautifully appropriate about ending a 26th century story with an open question. The twins are reunited, the fields are reanned, and the deepest mystery, the nature of charge itself, is still waiting. There's one more thing I want to leave you with tonight. One more thread in this story that I think deserves a quiet moment of its own. We've talked about how electricity and magnetism were born as strangers, grew up separately, and were finally reunited through the work of Ørsted, Ampère, Faraday, and Maxwell. We've talked about how their reunion revealed the nature of light,
We've talked about the field concept and how the space around every charge is structured and alive with invisible influence. But there's a deeper lesson in this story, one that goes beyond physics, and it has to do with the nature of understanding itself. For 22 centuries, human beings looked at electricity and magnetism and saw two different things. And they weren't being foolish. The separation wasn't a failure of intelligence or imagination. It was a reflection of genuine difficulty. The connection between the twins was hidden behind a technological barrier, the need for a steady current that nobody could have crossed before Volta's battery.
It was hidden behind a geometric surprise, the circular nature of the magnetic effect of a current that nobody expected. And it was hidden behind an asymmetry, the fact that only changing fields create the other type of field, that made the reverse connection even harder to spot. The universe was being coy. It was showing us two faces and challenging us to recognize that they belonged to the same entity. And for 2,000 years, we couldn't. Not because we were stupid, because the puzzle was genuinely hard. And when the connection was finally made, it didn't come from one person, it came from a cascade. Volta made the battery. Ørsted saw the needle move. Ampère worked out the mathematics. Faraday found induction and imagined the field. Maxwell translated Faraday's intuition into equations and discovered light. Hertz confirmed the waves. Each person built on the one before. Each one saw something that the previous one had missed.
And the full picture, the complete understanding, emerged not from any single mind, but from a conversation between minds, stretching across decades and continents. Faraday couldn't do the math. Maxwell couldn't have seen the fields without Faraday. Ørsted needed Volta's battery. Volta needed Galvani's frogs. And Galvani was inspired by the sparks from a friction machine that traced back to the rubbing of amber, the same amber that Thales had noticed 24 centuries earlier. The story of the twins is the story of human understanding itself. Slow, halting, full of wrong turns and missed connections, but ultimately, beautifully, triumphantly successful. We figured it out. We saw through the disguise. We recognized the siblings. And the world opened up. And if you're lying there thinking about what this story means, beyond the physics, beyond the history, here's one way to think about it. Every time you turn on a light, you're using Faraday's induction.
Every time you use a phone, you're using Hertz's waves. Every time you see anything at all, you're receiving Maxwell's electromagnetic radiation on the retinas of your eyes. The reunion of the twins didn't just advance science, it built the modern world. Nearly every technology you use daily, from the electrical grid to wireless communication to medical imaging, rests on the understanding that electricity and magnetism are one force. The discovery didn't stay in textbooks, it changed everything. And it started with a man rubbing amber on a piece of fur 26 centuries ago, and another man picking up a strange stone that pulled on iron. Two observations, two mysteries, one answer, hidden in plain sight for 2,000 years. There's something comforting about that, I think, especially at the end of a long day. The idea that understanding is patient, that it waits for us, that the truth about the world isn't going anywhere, and that even if we miss it for centuries, even if we walk right past the clues, even if our greatest minds look directly at the evidence and fail to see what it means, the truth just sits there, quietly, in the fields and the charges and the forces, waiting for the moment when the right person with the right tools and the right question comes along and finally sees it. The universe doesn't hide its secrets permanently. It just makes us work for them. And the work, as this story shows, takes many hands, many minds, many lifetimes. Thales needed Gilbert. Gilbert, despite his error, gave the subject structure. Franklin gave it vocabulary. Coulomb gave it measurement. Volta gave it flow. Ørsted gave it the crack. Ampère gave it mathematics.
Faraday gave it vision, Maxwell gave it unity, Hertz gave it proof.
Each one standing on the shoulders of the ones before, seeing a little further, reaching a little deeper, understanding a little more. No single person could have done it alone. The story of the twins is a story about what human beings can accomplish together, across centuries, when they keep asking questions and refuse to be satisfied with incomplete answers. So, as you're lying there tonight, settling deeper into your pillow, letting the day's tension drain away, think about this. Right now, at this very moment, the two forces we've been talking about all evening are everywhere around you, everywhere inside you. The electric fields holding the atoms of your body together, keeping the molecules of your blanket from disintegrating, maintaining the structure of every solid surface you've ever touched. The magnetic field of the Earth, threading through the walls of your room, through the floor and the ceiling, gently guiding compass needles in backpacks and glove compartments and ship bridges all over the planet. The electromagnetic waves carrying radio broadcasts through the air, Wi-Fi signals through your walls, infrared warmth radiating off your own skin, the faint cosmic microwave background whispering through the entire universe from the first moments after the Big Bang. All of it, every bit of it, is electromagnetism. One force, one set of laws, four equations, two faces of the same coin, reunited after the longest separation in the history of science. The twins are together now. They were always together, really. We just took a very long time to see it. Your nervous system is sending tiny electrical signals down your nerves right now, telling your breathing to slow, telling your muscles to relax. Those signals are electrical. They involve ions moving through channels in your cell membranes, creating tiny currents, tiny magnetic fields, tiny electromagnetic events, billions of them, every second. The same physics that Thales glimpsed in a piece of amber, the same physics that made Ørsted's compass needle twitch, the same physics that Maxwell captured in 4 equations, is operating right now in the 3 pounds of tissue behind your eyes, producing everything you experience, everything you think, everything you feel. You don't have to hold on to any of this. You don't have to remember the dates or the names or the equations. The story is there if you want it. Thales and his amber, Gilbert and his little earth, Franklin and his kite, Coulomb and his torsion balance, Volta and his stack of disks, Ørsted and his compass, Ampère and his driven brilliance, Faraday, the bookbinder who saw fields that the mathematicians couldn't see, Maxwell, the quiet Scotsman who wrote the equations of light, Hertz, peering through darkness at a spark too small to photograph. These are human stories. Stories about curiosity and persistence, and the slow, patient, sometimes frustrating work of understanding what was always right in front of us. The electric field in your nerves, the magnetic field of the Earth, the light from the lamp you turned off before settling in. They were always the same thing. They were always one. The universe just made us work for it. 22 centuries of work, from amber to equations, from confusion to clarity. And now you know. So let that thought settle. Let it be soft and quiet, like the hum of something very far away that you can almost hear if you listen carefully enough. The twins are home. The fields are real.
The space around you, the space that looks so empty and dark and still, is alive with invisible structure. Patterns of force laid down by every charge in the universe, reaching out to every other charge, filling every corner of space with direction and energy, and the ancient, elegant, endlessly beautiful physics of electromagnetism. You are lying inside that field right now. You have been your entire life. Every atom in your body is a participant in it. Every breath you take involves it. And tonight, you don't need to understand it all. You don't need to solve anything or remember anything or figure anything out. The fields will do their work while you sleep. The electrons will keep flowing through your nerves, carrying the signals that keep your heart beating and your lungs filling and your dreams drifting. The compass needles will keep pointing north. The radio waves will keep streaming through the walls.
The light from distant stars will keep traveling toward you across the vastness of space. Oscillating electric and magnetic fields leapfrogging through the void at 186,000 miles per second. Just as Maxwell predicted, just as Hertz confirmed, just as Faraday felt in the invisible lines of force that he, alone, could see. And here's one more thing to carry with you as you drift towards sleep. The electric field that holds the atoms of your pillow together, keeping the fabric solid, keeping the fillings soft. That field is the same phenomenon that Thales saw when amber attracted straw. The same phenomenon that Gray channeled through a dangling thread. The same phenomenon that Franklin pulled down from a thundercloud. The same phenomenon that Coulomb measured with his torsion balance. The same phenomenon that made Ørsted's compass needle twitch. That Ampère turned into a mathematical framework. That Faraday saw as invisible lines filling space. That Maxwell captured in 4 equations. That Hertz caught in a darkened room. All the same, all one. A single force, wearing different masks across the centuries, patiently waiting for us to recognize it. Your heartbeat is electrical. The signal that starts in the sinoatrial node at the top of your heart and spreads downward, triggering each chamber to contract in sequence. That signal is a wave of ions flowing through channels in cell membranes, creating tiny currents, tiny magnetic fields, tiny electromagnetic events. A cardiologist can detect those magnetic fields from outside your chest with sensitive instruments. Your heart is not just pumping blood, it's broadcasting, quietly, an electromagnetic signal with every beat. And in your brain, right now, even as you're drifting off, billions of neurons are firing. Each firing is an electrical impulse, a wave of charge moving along an axon, reaching a synapse, triggering the release of chemical messengers. The thoughts you're having, the drowsiness you're feeling, the way the story you've been listening to is slowly fading into something softer and more diffuse. All of that is electricity. All of that is charges moving through fields. The same physics, the same twins, together at last, working in perfect concert inside the 3 pounds of tissue that generates everything you've ever experienced. The twins are asleep now too, resting in each other's arms, inseparable, as they always were, as they always will be. You don't need to remember any of this. You don't need to hold on to the names or the dates or the equations. They'll be here when you want them. Thales will still be on the shore with his amber. Faraday will still be in his laboratory, seeing lines of force that nobody else could see.
Maxwell will still be at his desk, watching numbers fall into place with a beauty that made him catch his breath. They're all still there, in the story, waiting patiently, the way fields wait patiently in every corner of space. So let your breathing slow. Let your muscles soften. Let the weight of the day settle down through your body into the mattress beneath you. The fields are holding everything together. The charges are doing their quiet work. The electromagnetic waves are streaming through the walls, through the air, through you, carrying the whispered signals of a universe that has always been, at its deepest and most fundamental level, one thing. One force, one field. One beautiful, ancient, endlessly surprising truth, discovered piece by piece across 26 centuries of human curiosity. Sleep well, The twins will still be here in the morning.